exam practice?
Yeah, the exam practice. Did you go to the
Yeah, I did. It was kind of awkward because it was just me again. I was like, damn, guess no one wants to go. Guess no one goes to this.
The what was it? The SI
It,
session?
yeah, the SI session. I was like, oh man.
What time was it?
It was like from 8 to 10, which is kind of weird. He said it was from 6 to 8, but for some reason it was 8 to 10. I'm like, why is it so late?
Huh. Okay. So
Okay, so
practice exam, right?
yeah,
Yeah, we can do the practice.
like pretty much like all the stuff under the exam. Should we do the midterm exam first?
Yeah, I was going over, actually, I think I was going over the practice exam with Sai yesterday. But I think there were only like 1 or 2 questions I kind of got tripped out on, but
On this one?
yeah.
Okay. Yeah, multiple choice, short answer in programming. First one, which sorting algorithm will take at least time when all elements of an input array are identical?
I believe that was insertion sort.
Yeah,
And
insertion sort will do the check on the left. Shell sort requires it to like do the parts of it, like the 1 and
it cuts in the parts.
-1, that kind of thing.
So shell sort, merge sort is out of the question.
Mm-hmm.
I think I can understand you could probably get confused between selection or insertion sort.
I think selection you go selection's the one where you start at a position and then go to everything after it to find the max value and then put it in the current place and repeat that. And
I think the difference between insertion and selection is that in selection all the elements in the rear are sorted, but in insertion all the elements in the rear are unsorted in a way. And you just like go back and forth of putting it in. If I can remember that correctly.
Find the smallest element in the data, starting at position I, swap it with position I, repeat all elements. Oh yeah, well, insertion and selection I think are very similar. The left half is sorted, and the right half is unsorted. And the difference is that selection essentially finds the best candidate at each position, where insertion kind of just places the current element into where they should go in the sorted half. So like, for instance, kind of like if you were to sort a bunch of people in a line, like if you're gonna take a class and be like, okay, let's sort from greatest height to least height, and you have everybody stand in a line, as you're going down the line, you just swap people into the right position, if that makes sense. You kind of like starting from the first person.
Are these your typed notes?
Yeah, this is essentially his lecture slides, just copy pasted, but.
Okay. I was like, did you retype everything?
No, not really.
Okay, I was like, whoa, okay. That makes sense.
Yeah, insertion sort, assume there's a region of sorted elements at the front. Pick some elements at position J, insert the element into a sorted position at the sorted region. Repeat for all elements in the list. Yeah. So in theory, this would be the insertion sort, because if you have a sorted array, that one only has to go through once. Selection sort has to go through n squared number of times, worst case, or on average.
Because it has to go forward and then like bring that number all the way back, in a way, right? Or
it's because if you take, let's say for this example, it starts with 7, and it finds, or actually it doesn't start with 7. It starts by looking through the entire array and finding the smallest number, which is 1, and then it puts 1 where 7 is. It swaps them essentially. Then it goes to this position, and it finds everything in the array that is like the minimum in the entire array, which ends up being 2, so you don't do anything.
Oh yeah,
and you do swaps. 3, and then you look for everything. 3 is the smallest, so then you go to this position, which it finds 4 after going through the entire array, and swaps it with 4. Like, you see the pattern?
Yeah, that would be like of n times, you said, right? N times, or was it n squared?
because you're going through the array for every single time you're trying to find the smallest value, that is n, because you're going through every index, times n, because you're having to find the smallest value. So it's n squared. The actual,
Okay.
the function notation, like the, what is it, the tilde notation, I believe is n squared over 2, because you end up, like, if you get to the halfway point in the array, you only have to look through half the array.
Oh, so the tilde notation is a bit different on that one. Okay.
Yeah, the big O is n squared. The tilde is n squared over 2. And then as far as the insertion sort, it basically goes, okay, 7 sorted. Let's just start at 2. Okay, I'm going to swap 2 and 7. 2 is now sorted. Okay, I'm going to go on. I'm going to swap 3 with 7. 3 is greater than 2, so I'm not going to, I'm going to leave it where it is. Okay, go on to here. Okay, I'm going to swap 1 with 7, 1 with 3, 1 with 2, and 1 is at the start of the array, so it's sorted. Okay, 8, I'm going to swap 8 with 7, and it's sorted. I'm going to swap 9, oh, I don't need to swap it, so it's good. Okay, 4, I need to swap 4 with 9, 4 with 8, 4 with 7, and it's sorted. Okay, 6, I need to swap with 9, with 8, with 7, and now it's sorted. And then I'm done. Does that...
That's just n times. Yeah.
It's not n times specific, it's, at worst case scenario, it is still n squared.
Oh, it's still n square.
So, do you know if, apparently, I think, I saw another Discord, someone was asking why insertion sort was still n squared or something. Do you know why that is? So
I
essentially...
get the first. Oh, okay.
Oh, no,
You're saying?
go.
I get the first part of where it's like going through the array, so that's of n times.
Yeah.
And I'm trying to understand the second part of when it's going another n times. So I'm guessing, is that because the amount of comparisons that it has to do?
Yeah, we're measuring comparisons. N is the
So,
number of
okay.
comparisons it has to make, or swaps it has to make, either or. And think
Oh,
about
okay.
what is the worst case scenario for this array? Like for insertion sort, with the way that it is, you want to take, like, what is the best case actually? Best case is that it's in order, right? It doesn't have
Yeah.
to swap anything. It doesn't have to like move anything. Everything's in order. Worst case, it's in opposite order.
It's flipped, yeah.
Because every time, like let's say this was 9, 8, 7, 6, 5, 4, 3, 2. Okay, 9, 8, well 8 swaps with the 9. Okay, 7, well 7 swaps with the 9 and the 8. Okay, 6 has to swap with the 9, the 8, and the 7. So it has to swap with every single element that is already sorted. Which is every single element reminds you of the every single element, aka n. So it ends up being n squared, but the tilde notation for that is actually n squared over 2. Because on average, it only has to move it half the distance to the start. Does that kind of make sense? Maybe. Kind of.
So tilde for insertion would be of n squared over 2
Yes.
for that one also. Oh,
Yes.
so they both kind of have the same
The thing is, that's for
runtime.
the... Actually, is this one...
So for selection sort and insertion sort, it's n squared, and the tilde is n squared over 2
I
for
believe
both.
so. If we
Okay.
look...
And the reason why it's for over 2 is because if it goes to halfway point, that would be n squared. Yeah, okay.
Let's see. Let's just see the selection sort.
Okay.
Yeah, makes n squared over 2 comparisons and n exchanges. With insertion sort, where is that? It makes n squared over 4 actually. Oh, that's
Oh,
randomly. Actually, reverse input is n squared over 2. So this is the tilde notation for the worst case scenario.
Okay.
And best case is n minus 1 for tilde.
wait.
Although, actually, that's not tilde. That's just best case. Do you know why this isn't tilde? Yeah.
N minus 1 for sorted input. It's n minus 1.
Do you know why n minus 1 can't be tilde notation?
Tilde is like the closest, the tightest.
Think of what is tilde in comparison to big O?
It's tighter bound. It's more exact compared to Big O.
Yeah.
Big O's more of
But
approximation.
why? How is it, like, what is the difference between them? Big O is like, okay, let's take the dominant term, like the dominant expression of growth. So n squared versus n, or n to the power of n versus, or 2 to the power of n versus, like n to the 5th or something. Like, that's big O. But tilde is when we have some constant before that. So like 5n squared over 2, 5n over 2, or something like that. That's tilde. Whereas big O, we don't care about the 5 over 2, we don't care about the 2, we don't care about the numbers multiplied. But we still care about the most dominant term. So subtracting and adding in a tilde notation doesn't happen. If you have n and then you subtract some constant, we don't care. That's not tilde. Tilde of this function would still be n. It would just be n. Because we drop anything that is not the dominant term.
Oh yeah, damn, forgot about that.
Okay.
Okay.
Alright, so kind of as a practice, if you have the expression, let's think. Here. If we have what would be the big O notation of this versus the tilde notation?
Big O would just be 5n log n, right?
That's tilde notation. This
It's still
would
tilde?
be tilde notation. The big O of it.
Oh, wait.
The big O of it would be n log n. The only difference between them is we add a 5. Because we're multiplying the most dominant growth factor by some constant. Does that kind of make sense? And we also drop off the plus 5 because we don't really care. So
it's good review because, yeah.
Okay.
If we had that, it would still be the same. If we had that, it would still be the same.
It's the most significant growth, right?
Yeah, this is the most significant growth term.
Yeah.
And this is the tilde notation, but this is the big O notation. So you kind of think of it like, first convert your function to tilde, then convert it to big O. And that's essentially what you have here.
Just always remember to drop the constant in big O.
Yeah. Just think of it, it should be in terms of n and maybe to the power of an exponent, but that's it. Shouldn't be multiplied by anything, added to anything, subtracted by anything, nothing like that.
Okay.
Are we good on tilde
Yeah.
and big O? Okay. Then we have, okay. That was insertion sort. When dealing with the systems having low RAM capacity or analyzing large data sets, space is a premium. In these cases, algorithms must be designed to reduce their memory footprint. From the sorting algorithm implementation seen in class, which would be the worst choice? So right now we're basically saying, okay, which of these algorithms has to create more data, more memory when sorting? Which one do you guys think?
No, it's not selection or insertion.
Okay.
So it's definitely not those two.
So we're left with
So,
shell
yeah.
sort and merge sort.
Yeah. I thought it was shell sort, but then I said it wasn't, because apparently I thought, because with shell sort and merge sort, don't they both do it recursively in a way?
So
Because
what
like
you're
with
thinking of
recursion,
is
yeah.
I think I know what you're talking about. When you think of recursion, are you thinking of also like the method calls causing up memory space?
Yeah.
So in this case, we're not talking about method calls. We're thinking every call to a function has no cost on memory. Instead, what we're considering is there any point where we have to duplicate the data? Or maybe not duplicate the data, but duplicate a structure to hold the data. So we're creating new arrays or new lists, new trees, new anything to store the information that we're given. Instead of, because we know we're being given an array or in a list, right? That's true
Yeah.
for all these sorts. But it's not a given that we need to make a new structure to return. We could just return the same array, just modified. And that's what selection sort, insertion sort, and shell sort do. So shell sort is essentially insertion sort, but we apply some logic beforehand that's semi-sorted. Does that make sense? So if we go
Yeah.
to shell sort,
Because all shell sort is doing is just swapping between the length of the arrays, or the distance between them.
yeah, it's kind of like we take like every third of the data or something, and we kind of swap it in sorted order. We sort a third of
What is
the
that?
random data pieces, and then we do an insertion sort. So it's essentially like start by doing like some basic sorting information, then do a large sort. So if we hold on, I think there is a
so shell sort I'm kind of iffy on.
So I'm trying to remember what the runtime for shell sort was. I think wouldn't it be of, I don't know.
hold on. There was selection sort, each sort, where was shell sort? Shell sort. So it starts by, if you see it, hold on. Let me put this in slow motion. There. Or let's do a quarter speed. So it starts by doing some comparisons at like various points. You can see the red line is where it's currently looking at and doing comparisons. And you can also see the number of comparisons here. And you can kind of see how it's just doing large segments, if that makes sense. They're not looking at neighboring elements. They're looking at like, really, if I start at position A, 100 feet in front of me, I want to compare it with an element there. If that kind of makes sense. And then after it does that a few times, you can see that it eventually will run a insertion sort. Give it a sec.
So the distance gets closer and closer as it goes on.
Yes. You're essentially making it so that each time you go through, you're making it a little bit more sorted, but not completely sorted. Whereas if we go to insertion sort, this is insertion sort. You're essentially, as you're going to the right, you're putting the element in a sorted position. So everything on left is completely sorted. You can tell sortness by like how high it is. That wasn't obvious. So like, you essentially have this logic but you only do it at the very end. This is the like shell part of the sort. And then this is the insertion sort? Yeah. That last run was the actual insertion sort. But yeah. Do you kind of see the difference between shell sort and insertion sort? Maybe.
I see it.
Okay. And one thing you see is comparison, swaps, and reversal. Then you also have writes to auxiliary arrays here. I want to show you what merge sort does. Merge sort, an auxiliary array means they have to make a new array to sort it. And do you kind of see what array sort is like?
Yeah, so the only time when a new array is being made is when they're all merging together, isn't it? Because initially you're breaking down the array, and then once you start merging it, you make that new array, and you just plug it all together.
You see how in this diagram, you're breaking it apart, kind of? This is the merge sort. Each one of these like box arrays is creating an actual new array. That's when you're allocating new space and memory.
Okay.
Oh, so new arrays being made at every point then? So the first, second, third. Okay.
If you see it in the actual like source code here, sort auxiliary array equals a new comparable array of a length. And then you sort that from n-1. So then you have here, this is our actual like merge sort algorithm. You see a call sort. So we are actually creating a new array every single time. And we're creating an array of half the length at every point. But this algorithm only works when you break up the array by creating new arrays. However, there is, I believe there is versions of this where you don't break it into a new array, where you do it just based off of indexes. I think this is called an in-place one. Yeah. This is an in-place merge sort, where you can see there's no writes to an auxiliary array. You just do it using the original one, and you keep track of what indexes you're comparing. This isn't something we learned, but I thought it'd be worth mentioning that you can actually do a merge sort without actually making a new array. It's just not called merge sort. It's called in-place merge sort. Are you guys lost completely, or did you pick up any of that?
You mentioned it was in-place merge sort, so it's a little bit different.
Yes, it's a completely different thing. If he tests you on merge sort, he's not testing you on in-place merge sort. He's testing you on the one that requires you to make new arrays. And therefore is the worst choice in this example. Because we have low RAM. We don't want to use extra RAM just trying to sort something, so we'd rather choose another algorithm that is not going to have to create new arrays.
Okay, that makes sense.
Okay. Now 3.
Well, sorry. I think John was asking like, is the shell sort and what's the shell sort and merge sort? The big O and the tilde.
The runtimes.
Okay.
Yeah.
The big O of them.
Oh. I know shell sort. There's one that's like it's like unknown or something.
Yeah, he said it was unknown. He said the textbook author has spent almost 2 decades analyzing shell sort. He said still has not found the average runtime in shell sort. However, I believe.
Well, he doesn't. So we don't really know the runtime for shell sort.
Yes, but people have gotten it. They have kind of estimated it through runtimes. It's weird. It's like.
Oh, it's like that.
Oh, okay.
Yeah.
I don't think he's gonna ask us the runtime for shell sort then.
If he does ask you about it, just say we don't know, because that's what he taught us, and that's as far as he's teaching us in this course. That's what it is. Even though there is some kind of measurement of it to get approximately the same thing. It's just weird. You end up with this graph, which is not very nice.
Yeah.
Um,
But then for merge sort, if I remember,
merge sort does have a big O, I believe. Do you know it off the top of your head, or do you want me to say it?
I can remember. So the rays are being broken down. I want to say it's of n square times, wouldn't it?
At
Or
first, it
hold up.
does seem that way. It really does, but you got to realize where are the comparisons here. The comparisons are actually done right here.
Mm-hmm.
These are the comparisons, and then it's also done in a comparison when it's placing it into the array. So, at first, I believe it is, most people think n squared, but the only reason merge sort exists is because it is n log n. It is faster.
Oh yeah, because if you're going down the tree, then it's log of n times.
Yeah.
Okay.
It's weird. I think. Oh wait, no. I know why it is. It's because you're it's dual threading, multi-threading.
Okay, I don't.
It's divide and
Multi-threading.
conquer. It's divide and
Okay.
conquer. A divide and conquer algorithm thrives on the ability to do two operations separately at the same time. And therefore, if you were to just do this on a single threaded machine, and divide and conquer is the same as like selection sort, if that makes sense. Or not selection sort, as like insertion sort, I think. It would be n squared if you only have a single threaded machine, aka it can only do one set of instructions at a time. However, most of our computers, I'm sure your computer has more than one core, and therefore divide and conquer can be optimized in order to make use of that. And divide and conquer algorithms will try and essentially break up a problem so that teams can oh, your screen went right? Oh, can you hear us still?
You're good. Oh, hold up, Sandy. Oh.
You can't hear? Nope. You back?
Okay. Did you say what the it kind of went gray and like muted or whatever when or disconnected when you were talking about merge sort, Big O?
Okay. So
so we said n log n was the merge sort, and then what would be the tilde?
tilde for that. That's a good question. Did he ever?
So it's
Tilde
n log n
is
for the Big O for that.
Yes, it is n log n. I was trying to. I don't know how much you heard about me talking about divide and conquer, but
and then like then like it kind of went off.
Okay.
Fine. So
merge sort is a divide and conquer algorithm. And
okay.
Are you familiar with divide and conquer? Kind of, maybe.
Kind of. I wrote about it in the writing thing, but I got like half wrong. So.
Okay. So the difference between an elementary sort and a divide and conquer sort is divide and conquer is really useful because you essentially you're taking a problem. Let's say it's a complex problem, it's a difficult problem, and you're breaking it up. And you're breaking it up into two separate problems that are smaller, but make up the entire problem. And you essentially assign those two problems to different, like, an analogy for this is you have to sort an entire library, and you have a team of people sorting. So what you do is you assign each person to a different bookshelf. And once you, or a different stack of books, rather. And once everybody's finished their job, you all come back together and sort each set of books because you have your stack of books in order, so you just need to know, okay, who puts down their book first if you wanted to stack it better. So divide and conquer is you take the problem up and you split it apart into two separate problems and a different amount of problems. And that way you can do the same process at the same time, or multiple processes at the same time.
Okay.
So 2 people can sort of stack of books at the same time, which is faster than one person stacking like a large set of books, if that makes sense.
Yeah.
In programming, divide and conquer is typically you're assigning things to a thread or you essentially have 2 separate working threads. So one thread sorts 5 books, the other thread sorts 5 books, and your CPU. Most CPUs have multiple cores, and so you can do these operations at the same time. So both threads go into your CPU, and both of them sort your books, and then they come back to you, and you're able to sort the elements easier.
Keep bringing up threading. Did he ever mention threading in the notes?
It's not. I just like to represent it. I like to think of it as threading because that's the only frame of reference I have. I don't really I don't see where divide and conquer presents itself. That is in a real life scenario. Or like divide and conquer can be represented as, like, for example, the library analogy. But in computers, it usually is the concept of multi-threading. That is usually how divide and conquer is implemented. Because if your computer if you cannot execute 2 threads at the same time, it's considered single-threaded or single-cored, and single-threaded processes run at these, like if you had a divide and conquer algorithm like merge sort, and you run it on a single-threaded machine, it would be the same time to run it as if you were to run it as like a shell sort, an insertion sort. There would be no performance boost from using merge sort if you have a single-threaded machine. Because divide and conquer completely relies upon the fact that you have 2 sets of instructions running it simultaneously. Does that make sense? Kind of, maybe?
Yeah.
Okay. Yeah. Essentially, divide and conquer is better because you can, multiple things can be done at the same time. Multiple sorts, comparisons, swaps can be done at the same time. And that's where it comes into play. Or comes into... That's where its strengths lie. Okay.
So what's the tilde for the merge sort?
I don't think he put it on the slides. So let's look. Oh wait. Wait, this often gives an algorithm complexity log n. This represents performing a reduction in input size. Did he ever put it? Let's look. Merge sort tilde. See if this random PDF from Princeton.edu has it. I can't find it.
Okay, that's fine. Because I just he always loves like asking Big O and all that stuff. So
Yeah, it's more like you'll ask big O than tilde. However, tilde, when you usually ask tilde questions, it's because they have the same big O notation.
Okay.
Like, he'll compare insertion sort with selection sort. They have the same big O notation, but they have different tilde notation. Oh, different tilde, yeah. Like average, on average, they have different tilde notations. Like, selection always makes n squared over 2 comparison, always makes n exchanges. Insertion sort varies depending on your input. So worst case, it's n squared over 2. Best case, it's n minus 1, and it makes no exchanges. And on average, it's n squared over 4, which is faster. So at worst, it is the same as selection. At best, it is much faster than selection. It's a magnitude faster.
Okay.
Does that kind of make sense? Does that answer your
Yeah.
question? Okay. Do we want
Thank
to do
you.
number 3?
Yeah.
They go in tilde orders of the following code. The fragment is parameterized on the variable n. Assume that you are measuring the number of swap calls. Okay. So anytime we call swap, that's what we want to count.
I don't think you could tell the number of swaps for this. Oh wait, no, if I remember right, it was from yesterday, so I mentioned that you can't really tell. Because I remember correctly, it was because you can't really tell the amount of comparisons you're gonna do because it's random for the swaps.
Maybe. Hold on, let me look. Well, right off the bat, I see swap is in a for loop that goes to the n, like
Yeah,
n
I
amount of elements.
initially thought it was n times, but
I would say the worst case, absolutely worst case, not knowing anything about the data or this for loop, it would be n. But this if statement makes it very murky and very difficult to read, because we're essentially saying, okay, if z, some value z, which has to go through this array, or this for loop, is not equal to j, which j is essentially which element we're currently looking at. So, in I equals j plus 1, if j is less than n, I plus plus. Wait, oh, if z does not equal j. Z equals j here, so z would be 0. I is 0 plus 1. So this I is already different than j. And z is always, oh wait, I see what it's saying. So if the element at this position is less than the element we're currently looking at, z equals I. Okay. I see what you're saying with the, it's indeterminate, because depending on the data, you can't actually figure out what the tilde or big O is, or the tilde notation of it is. However, big O, we can decide what big O is.
big O.
Big O would be n.
Like, yeah.
I think.
No, it would be n.
Yeah. Because that's the worst case scenario. Tilde is a lot more difficult because we don't have much data or much information to go off of. Actually, this is a selection sort. This is just selection sort, I think. if the current value we're looking at is less than the value we're comparing, we're now going to set the value we're comparing to the value we're looking at. So this essentially says, okay, for every index, go through every index after it and find the smallest value and set that equal to z. And at the end of that, you're going to swap them. This is just selection sort. Do you guys see what I'm talking about? Do you see how that? Do you see where I'm getting that from?
Because it's comparing a of I, it pairs a less than.
Let's imagine we were going to label this, actually. Oh. Going back. I want to... Yes. So, this value is essentially saying the value we're currently looking at in this for loop. So we're essentially comparing, okay, starting from j plus 1, so wherever we are in this array, if j is 0, for example, this is j, sorry, it's going to look so, but we're essentially saying, okay, I is here, and then
I is plus 1. 0.
Essentially, let's imagine j0. I at the start will be this element. I after that will be this element. I after that will be this element. And what we're doing in this if statement is we're checking, okay, is the value at the current index I'm looking at smaller than the value I stored, which the value I stored starts at j, right? Right here. So the value we started at is this one. This is our starting value. And we're essentially saying, okay, is this value smaller than the one we're looking at? Is it? If it is, okay, we're going to make our z now equal to this one. This is now z. Okay, so is this one smaller? No, it's not. Okay, let's move on. Is this one smaller? It is. Okay, let's move. This is z, and we finished looping through the array. Now that we've finished, we're essentially going to swap j with z. So we just swap these two elements. And
oh yeah, no, I see it.
We proceed. That's how I figured out it was a selection sort, if that makes sense. Sandy, what about you? Do you get that confused processing?
It kind of my thing froze like when you were starting to explain it. Do you have this recorded, you said?
Yeah, I'm making a recording of this.
Okay, awesome.
Yeah. If you remember, selection sort goes through the entire array twice. Once to basically go like, if you're sorting something, you have to look at every place. And the second time it looks at it is to find the smallest value.
Okay.
And you can see this is our checking for the smallest value. Sorry.
Okay.
So this looks so ugly. I'm not used to using a mouse for this, but the first highlighted area is going through the entire array. The second one is going to find the smallest value. And the way we know it's trying to find the smallest value is this if statement. If the current value, which you can
Yeah.
is less than the value we have stored, which starts out at the current via a j. We're going to change the value we're comparing to whatever we're currently looking at. So we're going through the array until we find a value that is smaller than our z.
Okay.
Well, essentially, this is find this entire block is find the minimum value. That's how you can summarize this. Find the minimum value. If the minimum value is not the one we're currently at, not the position we're currently at, swap it.
Okay.
Does that make sense?
Yeah.
Okay. And the swap only happens the big O for the swap is n, because you can technically swap the entire array. The tilde notation is you have a best case, a worst case, and an average case.
Okay.
A best case, you swap 0 times, I think. A worst case, you swap n times. In average case, you'd swap n over 2.
Okay.
And because this is just a selection sort, we can look back at our notes and see if I was correct about that. So selection sort, it makes n squared over 2 comparisons, which we're not measuring, and it makes n exchanges. It's not tilde, it's just big O. So we were right about the big O notation. And we can also see, doesn't this look eerily similar to what we just had?
Yeah. Yeah.
You can see we have a min, instead of min it's z.
Mhm.
N, which is just array length, right? We have a for loop that goes from 0 to n minus 1, or in this case n. And then we have the j plus 1 thing. We have the less than, and if it is less than, set the minimum equal to the current position, which we have right here. And we exchange a with I, comma min. And the reason why this is n here is because we don't have a conditional for the exchange. You can see we don't check if I and min are the same. However, here we do. So it could be argued that best case, we don't make any swaps. Worst case, we make n swaps. On average, n over 2. Because if a data set is perfectly random, half the time we'll need to swap things. Maybe. Well, we'll just say, does that kind of make sense? Is that a safe assumption to make? I don't really know. Is it safe to assume that if you have like a... Oh, if you have
I was told to assume that you don't know the amount of swaps that you make because it is because it's unknown, because it's random.
Yeah, then
so
on average, we could put we don't know. Unknown. On average, we don't really know because we don't know the order of the data. But we know the worst and best case because we can make an assumption about the data, assuming all the data is in order or sorted, then we won't have to swap at all. Assuming the data is completely out of order, aka it's an opposite order, we can assume that it's n number of swaps. And assuming we don't know anything about the data, then we don't know the number of swaps. Does that make sense? I feel like that's something you could argue on your exam. Because it is a...
I can see what you're thinking. Yeah.
Yeah.
As long as you explain your thought process, like similar to what I just did, I'm sure he'll be fine with it, because as long as you understand that you recognize this is selection sort, but there's a twist on it, that if statement with Z does not equal J. As long as you recognize there's a little twist on what we previously seen, and you recognize what difference that makes, then I'm sure he'll be fine. I'm sure he'd give you full credit for this. I don't think he's expecting you to be able to analyze his entire function given an unknown data set or do an induction proof for it. Something ridiculous like that. Yeah. And here you could be like, it exists for this, but not average case. Are we good on 3?
Yeah.
Yeah.
Okay. For merge. If the merge method from merge sort was used for merging queues instead of arrays, how much space would be needed for auxiliary data storage? Assume the input is of length n and that all queues are internally implemented as a list. So trying to think.
Went over this, like all of this with the whole Psi yesterday. Yeah, he already told me what the answer was, and I think he said it was all 1 times. Because initially I thought it would be log of n or n log n, but
Yeah.
but he said it was all 1 times, and that was because can't remember how he explained it. It was just I was still kind of confused how he explained it, but
did he mention that because it was a linked list rather than an array, you didn't have to recreate in the array or something?
Arrays. Auxiliary. Yeah, he talked about it being a linked list, but then it only said something about arrays though.
So what I'm assuming is that because it was a linked list rather than an array, you could just be like, okay, swap these nodes rather than swap these indexes. This is weird.
Yeah. And enqueuing and dequeuing, you can do that with an array though, can't you? Well, queues, I mean.
Let's look at
So like I was really confused why he would bring up linked lists, because like it's only mentioning about arrays though, which is weird.
Yeah. Well, it's talking about memory, right? How much space would be needed for auxiliary data storage? Oh, I see what it is. Okay. So I think I know what he's talking about. So you see this image?
Yeah.
Imagine instead of making a copy of the array, you just separated it. You just drew a knife and cut between the two. And now you have 2 separate arrays. Then you did it again and again. And you did it 1 more time. That is what a linked list is, doing when it removes the node that is like next or previous. When you sever the connection between 2 nodes, they become 2 separate lists.
I'm just wondering, at what point does he mention about a linked list though? Because like it all says arrays.
With a list. When they say list, they're referring to non-array. So instead of arrays.
Instead of arrays, how would
instead of arrays means anything that is an array. So assuming linked list or list. And it says internally implemented as a list. And usually when they're talking about list, they mean a linked list.
That's so the wording was so off. Okay.
Yeah.
That's rough.
Yeah, that is. Yeah, that wording is off.
Yeah.
Yeah, but do you see why it's O of 1 now versus the?
Yeah, I get that it's O of 1 because of the linked list. I just didn't understood what point did it even talked about linked list.
And
yeah,
I think this is interesting though, because let's say you have a linked list and you want to do a divide and conquer algorithm versus an array. An array in Java, you know the length of it by doing like array.length. And in Java, if you have an array of 8, size 8, even if you only use 4 spaces, it's still size 8. And a linked list is only as long as how many nodes are connected in it, right? And so if I have a linked list of size 8 and I sever the connection between the 4th and 5th element, I now have 2 separate linked lists of size 4. And therefore, if I were to do some sort of merge sort on it, it would then do the same process for a linked list of size 4. So the indexes 2 and 3, you sever the connection there. And then you apply merge sort to that. And the indexes 1 and 2, you sever the connection between those, and you swap them if needed, essentially. That's where the sorting part comes in. I think it's an interesting. I never thought of a linked list implementation of merge sort. I always figured it was an array, which I think actually is it a rotate merge sort?
This is definitely going to be on the test.
What, the merge sort stuff?
Oh no, this question. Like, because he like makes like some of like the same questions on the test sometimes.
Yeah, this is
like
his practice exam, so.
Yeah, but like sometimes he puts the same questions.
Oh yeah, that is fair.
On the exam.
This is definitely something to watch for, because when they're talking about, anytime they're talking about auxiliary data storage, auxiliary just means you need to
new memory.
Yeah, you have to create new data structures in order to sort things, or to in an algorithm. Auxiliary is essentially like a helper data storage that you can do whatever you need to do.
Okay.
So like new priority queue or new array or like new linked list, those are like
you
all
have to
auxiliaries.
make some new data storage structure. I don't think we really count like creating 2 variables or 3 integers or numbers. It's more or less referring to you're creating a new array of variable size. Variable size is essentially the key word there. If you're creating space for something you do not know the size of, regardless of data or input data. So like, regardless of if you're given an array of 100 or 1,000,000, if you cannot say the size of the data the amount of space you're allocating, then it's auxiliary. It's auxiliary data storage is needed, because if the amount of space you're allocating to solve the problem depends entirely on how big the input data is, then you need some sort of auxiliary data storage. I don't know if that makes any sense, or if that maybe, did I confuse you?
No, it makes sense.
Okay. Are we good on this one?
Yeah.
Yeah.
Okay. Yeah. Good.
Okay. 5. If you had to pick a data structure on which you would be performing merge sort, which one would you choose? Hint: think about minimizing space usage. So we have an array, a linked list, a priority
that sounds
queue,
pretty obvious.
or generics.
Yeah.
Well,
I think it would be linked list. Because, yeah.
I think, does priority queue?
I don't think.
That's an
Well,
ADT.
it says that you to pick it says pick a data structure. I don't think priority queue would be a data structure, because you can still represent that as like an array.
Yeah, I think these two are red herrings.
Yeah.
Generics is not a data structure. It's a concept.
And you got your top 2. And if I remember correctly, with the arrays, you're making new auxiliaries, and you're just modifying. You're making new arrays after that.
Yeah.
So it would be linked list.
Yeah, I would say linked list as well.
I don't know. I think that one would be pretty easy.
Yeah. You good, Sandy?
Yeah, thank you.
Okay.
The lower bound proofing for sorting. Why must there be an n factorial leaves on the decision tree? Oh, this goes back to the decision tree. The one in module. I can't remember what. I think it was in the priority queues.
The n factorial leaves on decision tree. A decision tree is like given a scenario. Each leaf is essentially okay. I made a decision. What decisions can be made after this is the other leaves, and
if you pull up the priority queue module, it'll show you like what the tree would look like. Yeah, that one further. Oh, you passed it. That one right there.
This one.
Yeah. And so out of all the decisions at the bottom, so if I remember correctly, it was you'll have the n factorial decisions, and out of n factorial, it would be one right answer to that.
Yeah.
If I can't.
There's one right answer to a decision tree. I think for every because you have to. Well, I'm thinking.
So yeah, one right answer. Yeah.
If this is comparing swaps, swapping or comparing, this is just swap or comparisons. Comparing 0 and 1. If it's sorted, then you got to go to 1 and 2. If it's sorted, okay, I see.
Yeah, and you have you have n factorial decisions, and then you only have and out of n factorial decisions, there's one right answer. There's only one right solution to your to your decision.
Okay. The way I see it as well is when we're not, I don't think he's asking for a complete decision tree. I think he's just talking about the lower bound proof, which is like what is the fastest we can do it. So it is like how much for the right decision. How much why must there be at least n factorial leaves on a decision tree? Okay, so when we're trying to solve the lower bound proof, why must there be n factorial leaves? And isn't a decision tree a complete tree?
I think it can be an incomplete tree.
Okay. Oh, yeah, this is incomplete, so. I guess. I'm going to pull up the module slides. Let's see if it was better. This was part of sorting merge sort, so. Isn't this supposed to be n equals 3? I can't remember. Because it's an array of 3. I think so. So how many leaves does this have? This has 1, 2, or this is 3, 4, 5, 6, 7, 8, 9, 10, 11. right?
Yeah.
I was told by Sai you don't really have to come up with the whole tree, but just understand that the amount of decisions that you have to make and the amount of solutions that you can pick from.
The amount of
But
decisions you have
I
to
don't.
make and the amount of solutions you get to choose from. Is that what you said?
Yeah.
Oh, because there's n factorial ways of ordering the
Yeah.
array. That's it. Oh, because an array of size 1, 1 factorial is just 1, and therefore it's only one way of sorting an array of size 1, right? If you have an array of size 2, you can either have two possible outcomes. It's one book is on the left, one book's on the right, and the opposite of that. Those are the only two options. 3 factorial, there are 6 different ways of ordering it. If every book is unique, there's 6 different unique orders. Essentially, yeah. Right?
Yeah.
Okay, and then 4 factorial, there should be 24 different ways of ordering it. Okay.
And then out of those 24, I think one of them serves a solution. Is what I remember correctly. Yeah.
Oh, it's because it's like, okay, if we have like a space of, let's say we have an array of 1, 2, 3, 4, and 5. If we were to look at the combinations that you can put at position 0, you have n number of numbers that can be placed there. And then what about this position 2? Well, the first position, something is already there. So, but everything else is fair game. So it's just n number of book or things there are plus -1, right? So like if you have 5, or if you have 5 books you got to order, one of the books will go in the front. One of the remaining 4 will go in the second place. One of the remaining 3 will go in the third. One of the remaining 2 will go in the third spot, or the fourth spot. And one of the remaining 5 will go there. So, and this continues for however many, however big your data set is. And if you think of this, this is just n factorial. Factorial is just itself plus itself -1 until you get to 0. So if this is 5, it is 5 plus 4 plus 3 plus 2 plus 1 plus 0. Right? Then you have. Does that kind of make sense? All right, not minus this one.
Yeah. Yeah. I see where you're going at.
Is that what I did I do that right? Or am I thinking of multiplying? I think I'm multiplying actually. A sec. Oh, I have a 0 there. There.
Okay.
It's because there's, let's say you take the first book, there's now, there's n-1 times, oh, it's just factorial. I don't know how best to explain. Do you guys kind of understand how that relates?
Yeah.
At least mathematically you can see it, but physically, if you have 3 books, if you take one book, there is still 2 other ways of ordering the remaining 2, and so you end up with 3, because there's 3 possible books you can put in the first spot, times 3 minus 1, so 2 possible ways you can order it in the second spot, times only 1, because there's only 1 remaining book that people don't have. I don't want to confuse you. Ignore what I just said if that confuses you. But
should we just like kind of explain it by like how you just wrote it just now? In terms of the fact, like, you know, kind of write, I don't know, explain it in words.
I was just gonna say that there's gonna be n factorial decisions that you can come from.
Well,
and
he's asking why there's n factorial. So you're starting with n factorial. I would just say that it's because of the nature of sorting. There's n factorial ways of sorting a set of items of n size. If they don't, like, if none of them can exist within the same place, and we're not leaving gaps out, if we're not allowing gaps, you can only order them n factorial number ways to have a unique ordering of the books, essentially. The way you'd explain it is just by explaining why it's factorial, which is the...
So there's n factorial ways of sorting it.
Mm-hmm.
Okay.
I think if you show some kind of math like this, you kind of get, well, he'd probably want you to explain this part. I'm trying to think of the best way to explain this. How would you guys explain this? If you were given this right now, what would you go with?
Honestly, probably what I would have said before.
Which is?
Which was that there would be n factorial ways of sorting it, and out of the n factorial ways of sorting it, one would serve a solution.
Okay.
Is that what Sai said yesterday, or?
Yeah, it was kind of what I was talking with Sai, and he said he agreed. He actually added some more input to it, which I can't remember what he said. But I just wanted to keep it simple because I wasn't too sure. Like,
fair.
Yeah.
I would say the way that I thought of it is that if I were to explain this online exam, I would say because there is an n factorial ways of ordering n number of elements, and so that each outcome is completely unique, we end up with n factorial. That's just something. That's just like a factual statement, that if you have n number of elements, you can order them uniquely in n factorial number of ways. And with a decision tree, you have to look at each possible outcome to decide, okay, to decide what order they should go. Because only one of those ways is going to be right, depending on your data set. And therefore, out of this, every possible outcome, there's only one of them that is sorted. Or, assuming you have no duplicates. If you have duplicates, then there's more than one, but that's different.
Okay.
Okay.
That one?
Yeah, we're good.
Okay.
Yeah.
What is the difference between a max heap and a priority queue? So the one answer is a max heap provides ways to both add and remove elements, but a priority queue does not. B, a priority queue requires O of n time to remove an element, while a heap works in log n time. A heap is how data is structured, while saying priority queue specifies what operations can be performed. D, there isn't any difference. They're different names for the same thing. So,
I think it's C. Yeah, it was C.
Okay. And let's
And
explain by knocking out the other ones. So why would it not be A?
because you can still add and delete with priority queues though, even though it says it does not. So that doesn't
Okay.
really make any sense.
So that's why A
And
isn't right.
yeah.
B.
And priority queue requires O of n times to remove an element while a heap works in log of n times. I believe the runtime would still be the same depending on the cases for one of them.
Well,
I don't know. I don't know if that makes sense.
because priority queue or a heap is a priority queue, but a priority queue is not a heap. Therefore, priority queue does not have a big O notation. Why? Because it's describes the functionality of something. It does not describe the time complexity or the operations needed to perform something, if that makes sense. Like a merge sort is an algorithm and it describes how to sort something. Whereas
You erase the data.
an array is the data type. It's kind of like, what's the difference between an array and merge sort?
Okay, so one tells you the operation, the other one just the structure of it.
I bet actually, I think I take that last one back. It's what's the difference between a list and a linked list? It makes very little sense because a list describes functionality. A linked list is a specific implementation of that functionality.
Okay.
Anyways, yeah.
So you're saying a heap is the data structure and the priority queue is what happens in that data structure.
If we were to draw, like for what's a priority queue? Priority queue. What is considered priority queue and what is considered a max heap? We essentially have a heap. And what you end up with is a heap.
So with a priority queue, doesn't it have like functions like sync and swim? Yeah, sync, swim, delete, and swap and all that stuff. Or not swap, but and with the max heap, it would be what the tree would look like, being the most significant figure at the top, and then the greatest and smallest to the right and left.
Yeah. So a priority queue or a heap is a type of priority queue, and a max heap is a specific type of heap. So a max heap is still a priority queue. It's a specific implementation of it that uses a heap, and that specific implementation is sorted by maximum value. Priority queue only means that there's a sortedness to things, if that makes sense. Like so key concepts is that it has an insert that adds a new element to the ADT, and a del max, which removes the largest or something equal to it element in the collection. That is a priority queue. That is the definition of priority queue. Tells us nothing else. All we need is the highest value and a way to insert a new element. Now a heap can be a few things. Heaps can be made in arrays, it can be in a linked list, doesn't matter. It just varies. It could be in a list, something like that, or a tree. You can see also here, a PQ is a heap, a bin tree, which can also be made in an array, or using an array. Remember that representation is not structure, right? So in this instance, priority queue requires O of n time to remove an element. That's not necessarily true, because if I told you implement a priority queue would you instantly know, oh, I can do that. I know the instructions required to do that. Or would you be like, okay, first I need to choose what kind of priority queue I should make? Which of those sounds more likely?
I think the second option.
Yeah, you basically have to decide what kind of priority queue I want to implement. And that's why it can't have a big O notation. With a merge sort, if I implement merge sort, you'd be like, okay, I know exactly how to do that. I don't need to make any other decisions, as long as I know the input data or whatever. But a heap, the max heap does have some logic behind it. And we may know the big O notation, but because this doesn't have a big O notation, it's safe to say, okay, this is the reason why this is false. Because they're trying to give us some time complexity for something that we don't know how it's implemented. It's an ADT, it's not a algorithm, if that makes sense. Are we good on why B is wrong?
Yeah.
Yeah.
And then let's talk about why D is wrong. There isn't any difference. They're the different names, the same thing. Why is that not technically true?
It's just what you kind of drew out just now.
Yeah, it's that a max heap is a type of priority queue, but a priority queue is not a max heap. They're not the same thing. They're not synonyms for each other, but yeah. And then C, I meant, is the one that we think is right. So a heap is how data is structured, which is true. A max heap is describing how it's structured, while saying priority queue specifies what operations can be performed. Like we were saying before, it's an ADT. It doesn't have any implementation or algorithms associated with it. It just has a list of operations you can do on it. So yeah, C and B is the one I have. Both because we eliminated all the wrong answers, as well as because we know the reason behind the right answer. Maybe it was redundant to knock out the rest of them, but that's what I like doing.
No, it's actually really helpful.
Yeah. Well, I usually do on the test too. Yeah, that's how I usually do it too. You just kind of pick out all the wrong answers.
Yeah, I also write down why it's wrong on the side, so if I ever go back to it and be like, oh, that's my thought process behind it, that's actually wrong. I accidentally made a mistake, and I realize it later on, as well as it helps me think through these answers, because like, if you write down your thought process, even if in the moment you don't think it's wrong, if you later down the line see another question related to it, and you're like, oh, that thing was wrong. Writing down that thought process kind of keeps it in your mind a little more. That makes sense.
I got you.
Hold on. Okay. Consider this array representation of a heap. What is the right child node of 75? Assume the 0th index is null. So, what is the right child of node 75? So, node, we assume, like, almost tree-like structure. We know it's a heap, so it visualized, you can see it like a tree, but it's represented in an array. How do we figure out the right child of a node? Do you guys know?
Can draw it out like I think you can draw it out like a tree. So try drawing out your tree first.
Yeah. So.
Yeah. Initially, Sai said that there's some math that you can just do behind it, where it's like 2k plus 1 and 2k.
Yeah, you can.
And 2k plus 2. But I don't know. I kind of got confused with that, so I thought drawing out a tree would make more sense to me.
Fair. If you look at how the information is represented, you can make inferences on like how you use math to figure out. Oh, it's not using that. Use math to figure out what it's supposed to be. So we have blank 100, 75, 50, 51, 40, 30, 3, 25, 10. this over here. So we put 100 here. 75, 50. Uh, 40, 30, 3, 25. Is it? Am I doing this right? Hold up.
You got it.
Looks
Yeah, you got
right.
it. You got it. You got it.
Okay. 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 And if we were to draw this kind of like how it's represented in the array, we'd have a empty box.
Wait, I think you're missing a number. 25.
Am I?
Yeah, you skipped over 51.
That's why it looked wrong.
Yeah.
I was like, this looks weird. Sorry about that. Taking a little bit of time to draw it out, but yeah, doesn't really matter too much. But and delete this one. There. So you can kind of see how there's empty bubbles here. We're drawing connections, that to that, that to that, bam to bam, this to that, that to that. Okay. So the problem asks from 75. So from over here, how do we get to the right child? So this is 0 index, 1, 2, 3, 4, 5. So how do we get from index 2 to index 5? Y'all know?
So to find the right element, I believe it would be 2k plus 1.
Yeah.
Yeah, it was 2k plus 1.
So if we think about this, this is 0, 1, 2, 3, 4, 5, 6. I forgot to draw that. 7, 8,
And
9, 10. Don't worry about this.
oh wait, I think I do see the math behind it actually. Yeah, and you just like put the position of whatever 75 is into 2, so 2 times 2 plus 1. Okay, and then if you multiply it by 2, you get the left position. That'd be 4. Okay, I think I see it now.
Yeah, so given any node, k, multiply it by 2. What do you get? You get the left node, left child node. So 6, or index 6 in this instance, and 30 is the value there. But we want to get the right one. So all we do is
Yeah.
add 1. And what about 7? Well, I'm at 7, I want to get the right node of that. So times by 2, 14, plus 1, 15. Do you see how, you can kind of see how we got there. So from index 2, 75, to get to our right child node, we multiply by 2, 4, plus 1, 5. We get to 40. That's why I spent so much time drawing it out. Does that make sense?
Okay. Yeah. And it actually helps us draw it out because, like, when I saw this, my first guess was 51.
Mhm.
And then, like, yeah.
So,
the way I kind of saw it as, so, I wonder if I can write, damn. It
How did
was,
you see it?
here, can I share screen?
Yeah.
Share your screen. Sorry. You guys, actually, hold up. Sorry, I haven't changed window. I have like two monitors up. I'm not sure which one you guys are looking at. Let's see.
Hold on, I think I'm
Here,
trying
we'll
to
look.
move this onto the, I have a Discord popped out, like, to see your screen, but I think it's on my third monitor, which is on my TV. Oh, it's not. That's just broken.
My desk ain't big enough for a third monitor.
Well, mine isn't either. It's my TV, which was off, so I couldn't see it. But, okay.
Okay, so let's see. Where's? Dang, I had my.
I can see it.
Damn, I just moved it. Okay. So let me just. Let me pull up one note. Yeah. So here's just a bunch of code I wrote up. So let's say you're trying to grab. Let me put my drawing. So let's say you're trying to grab this position right here, right? 3.
Mhm.
And so the way I initially saw it is that you start from here, right? And you underline it. And since these two are connected to each other, so you underline these two right here. And that's the second row. That's the second column. That's the second column, right?
Yeah.
I mean row. And then you go down further even more. The third one would be all this down here. And so then it just gets bigger from there. So like whatever element you have in here, it just gets bigger and bigger and bigger. So like so the child element would be like would get larger and larger and larger for the array. Well, not for the array, but for like for the God, I'm really bad explaining this.
You're essentially snapshotting an entire height, like all
Yeah.
the elements at a certain height. So height of 1 is just 1. Height of 2
Yeah.
is 4 and 10. Height of 3 is 2, 3, 6, and 8. And the way you determine that is you take the length of, starting from height of 1, you take the length of the height of the area you're underlining. So like, so you're, and for 1, you only underlined 1 node. And essentially you multiply that by 2 to figure out how many nodes I need to underline after that, right? So you had to underline 4 and 10. And then, okay, how many do I have to underline after that? Well, how many nodes are in 4 and 10? Well, 2. So I underline 4. 2 times 2 is 4. So you underline 2, 3, 6, and 8. Well, how would I figure out after that? Well, how many nodes are in that layer? 2, 3, 6, and 8, that's 4. 4 times 2 is 8. So I know there's 8 elements in the next layer. You essentially just recreated k times 2. And in order to find what you're getting is, like, for instance, index of 1 is 1, times 2 you get the index of 4. Well, the index of 4 times 2 is the index of 2. So aka the start of the third layer. And the index of 2 times 2 would be the start of the fourth layer, essentially, which we don't have on this graph. But
yeah.
Yeah, I see what
But
you're saying. It works.
yeah.
Uh,
So there's like there's like a bunch of ways you can go at it, but you know, yeah.
In theory, if you just mark down the indexes, if you write down the indexes of the array, you can just do math for left and right, but whatever is easiest, obviously.
Yeah.
For me, I personally think it would be easiest to just do 2k plus 1, or 2k.
Yeah, no, that part looks pretty easy. Yeah. I just didn't recognize it.
So knowing this, index 0, index 1, index 2, 3, 4, 5, 6, 7, 8, 9. And so we're looking for 75. We're looking for right. Right is plus 1. Or 2 times 2 plus 1. So 0, 1, 2. 2 times 2 is 4. Plus 1 is 5. So 0, 1, 2, 3, 4, 5. 40, which ends up being C. And if we look back at the diagram, 2 to 5, which is 40, which is right. Does that make sense?
Yeah.
Yeah.
Okay. On number 9. One of the main operations for PQ is to move an element lower in a heap so that it will be in a particular or proper order. So it is implemented by the sync method. According to lecture, this particular implementation takes log of n number of exchanges to put the element in its proper place.
You should point out the cost metric of this. So the while loop is 2 times k, so that makes it a log of n times. And let's see. And the amount of comparison, you don't.
Well, it's asking you support this claim by explaining why it's log n. Why is this log n? What about this tells you it's log n?
I just understand that log of n would be when your variable is being multiplied or divided.
Exactly.
So 2 times k
when
is log of n.
The distance of the end, aka as your the distance of your end goal gets shorter as you like traverse it, if that makes sense. So that's if you're multiplying it by a value, so like if k is times 2,
the distance is increasing.
This distance is increasing not linearly but exponentially. Then we know it's a log, because log is just the opposite of an exponent, right? Log base b of n is just what is it? B to the power of no, I forget the wording for it, but log is essentially the opposite of an exponent, and so anytime you have exponential growth, you know it's going to be log of time to finish. I don't know if I just confused you more, if you understand about it.
Yeah, no, I got it.
Okay. What about you, Sandy?
So, actually, this really cleared it up for me because, like, I'm always kind of confused about the whole log and everything. But yeah, this makes sense now.
One thing I do notice is, I think I told you this before, but he likes to do, on one of the tests he's had like a for loop. It goes from 0 to 100. And I is increased by 1. What would be the big O of that?
Oh yeah, I remember one of those questions. I think I got tripped up on those too. I is increased by 1, and this until it hits 100.
Yeah, so I equals 0. I is less than 100. I plus plus. Let's imagine we have this for loop.
Oh, then wouldn't that be 100? Because like, yeah, wouldn't it be like to 100? So like, you're doing 100 operations.
Like big O notation does. We don't care about constants. We take the largest number.
Ah.
So
then,
if you have
it would be
f of n equals 100, the big O of this equation would be 1. Because we don't care about the 100. But if this is tilde, tilde f of n would be 100 still. Does that make sense?
Damn, okay.
Kind of.
Yeah, no, I see where you're going at. So if I remember, so like, yeah, because tilde is the close approximation of it, right?
Yes. It's the
Okay,
closest
yeah.
approximation to the largest increase.
Okay.
Or the largest factor, yes. It's close approximation to O of n without being O of n.
Yeah,
Wait.
and O of n is the most dominant or the most significant?
Yes. Essentially both. Both the most dominant and significant term. We don't care about how precise that significant term is. We just want to know how a factor of which it's growing. Like back to this, right? We only care that it's growing by n log n. We don't care that it's growing by n or log n or 5n log n or a million n log n. We don't care about that. We only care about n log n. So in this case, we don't care that it's 100, a million, even if it's 2 billion. We would still put O of 1. Even though it's 2 billion, it's O of 1. That's just the nature of big O notation. However, tilde would tell us it's 2 billion. It tells us there is a really big, it's a better approximation than big O notation. Because if we know something is O of 1, we know that it's the same amount of time no matter how big our data set is fed in. Whereas tilde, it'll tell us exactly how many times, or a better approximation of how many times we do an instruction given any arbitrary data set. Better understanding, worse understanding.
Better.
No, I see where you're putting it at.
Okay.
Yeah.
So in this case, this is log n, and the reason is that there's only one growth. The only thing that has to do with n is right in this while loop. Now, had we put a for loop around this or something, this would be different, right? Let's say we have a for loop around this that's for I equals 0, I is less than k, or something like that. That would change this to be O of n log n, if you can kind of visualize that in your head. Maybe.
I'm sorry, what did you say? It would change it to what?
N log n. So n times log of n.
Oh, I get where the log of n is coming from. To point out where the n times is coming from
would be
is that
for loop. That would. So if it was, I'm saying this is not the actual problem. Don't look. I was.
Oh, okay.
Hypothetical.
Okay.
Sorry if I confused you. I meant
if there was a for loop though, that would be an n log n times, but it's just the loop. Okay.
Exactly. Right now it is log n. That's a fact. And we're trying to support that claim, and the way we do that is explaining that it's exponential growth. Therefore, it is exponentially getting closer to the desired outcome, essentially. Closer to the program's termination is the specific way of saying that. And if it's getting exponentially closer to the program's termination, then we say it is log of n times whatever. As far as the tilde notation, I'm not entirely sure, but if we were to, I think it's still log of n, because you still exchange every single time you're going through. What were you gonna say, Sandy?
Oh no. If it's divide, then it would just be exponentially decreasing then.
Yeah, so that wouldn't that still be log of n times if it's exponentially decreasing?
If it's dividing, what do you mean by that? Like if you're trying to get to 1 and you start at 100 and you're dividing by 2 every time, in that case it is log of n still, because you're exponentially decreasing, but you're in the grand scheme of if you're starting at 100 and going to 1, there is a distance you have to travel to get to 1, right? For any distance,
Yeah.
going from point A to point B. If you're going exponentially closer to point B, I'm moving my hand even though you can't see it. If you, like, shapes. You have a line from point A to point B, and you are getting exponentially closer. Oh, actually, yeah, exponentially closer to the end goal. It's log n, right?
Yeah.
But if you're going linearly, this is just n. Does that make sense?
Linearly being it's like increasing by 1, or
Oh wait,
what you're saying?
I think this is exponential that I'm showing here. I think. Hold on, let me erase this really quick. The bottom half of this is linear, where you're moving the same distance every time. It's not getting faster as you go on. You think of it kind of like a race. Are you getting exponentially faster as you run to the finish line, or are you just running the same 5 miles an hour every time? Because if it's 5 miles an hour every time, then it's n. But if you have a jet booster on your back and you start from 1 mile an hour to 2 miles an hour to 4 to 8 to 10 or to 16 to 32, you are getting much, much faster, which looks something like this.
And that's what the multiplying, right?
This is our log n stuff. This is multiplying or dividing. As long as you're multiplying towards your end goal or dividing towards your end goal, you are getting there exponentially, like, faster.
Okay. So dividing is still log n. Okay.
Yeah. Dividing and division and multiplication are opposites of each other. So as long as you're moving in the it's the same thing. It's the same thing.
Yeah.
Okay.
There are instances where you're dividing and you'll never actually reach your goal, and therefore it is infinite time, right? Because if you start off going there's a classic problem of, like, if you stand in front of the door any distance away, let's say 5 meters, and you were to go half that distance between you and the door, then you'd be like 2.5. And if you kept doing that, you'd never actually reach the door, because you just get closer and closer and closer to being 0 meters away from the door, but you'd never actually reach it. At some point, it'd be super immeasurable that you can't even tell how far away you are from the door. It would look like you're at the door, but if you kept going down, you'd never actually be at 0. It's a paradox, essentially. But we're assuming that he's going to give us algorithms that doesn't happen. That doesn't happen. I would just be wary of that. If the math doesn't look like it's right.
Okay.
Alright. Are we good on that question?
No.
Yeah. What?
You did.
What was that? I had trouble hearing.
Oh, it makes sense.
Okay.
What you just said.
So, step 10.
These are all ADJs. So,
we go through the steps of ADJ to create a solution for a given problem. What should we do if we find in the justification that our solution does not satisfy the metrics defined in analysis? So,
that'll be B.
Well, let's look at them first. A, skip those metrics and just include the ones that are met. It isn't important to meet all the metrics as long as we gave a solution.
That's false.
That's false, but why is it false?
We need to meet all of them.
In our justification, we're comparing ourselves with the problem and other solutions, right? We're justifying why we chose this approach. We shouldn't just ignore our downsides. Like, if I said, oh yeah, for for when choosing a design that's memory efficient, we should just use merge sort with an array, because merge sort's really fast with arrays. You think, well, that doesn't answer the problem. The problem is memory, and merge sort with an array uses a lot of memory. That's an issue with my justification. That's why A isn't right, because we can't just skip over the fact that it doesn't meet the requirements. B, loop back to the design phase and either modify our solution or create a new solution that satisfies the metrics. That could be that's arguably good, because you say, oh, you can modify it. So let's say, okay, well, instead of merge sort on an array, let's do a linked list, because a linked list is better memory efficient, and therefore we can design an algorithm that is more memory efficient than an array-based implementation. That's a possible answer, I would say. But before we choose that, let's look at C and D. So, back to analysis and modify the metrics to match our solution. Well, we probably don't want to modify our analysis, because our analysis breaks down the problem and makes it so we understand what we have to meet. What are the standards we have to meet? What are people asking of us? We can't just be like, oh, let me erase the bit where they asked us to make it memory efficient. That won't have any problems, right? So that's why C is wrong. It's just, you can't just forget about your problem. And then D, skip the justification step altogether. The most important part is the design phase. That's just altogether a bad idea.
Yeah.
I don't need to justify it. It's wrong, but I don't need to justify why it's wrong. All that matters is I have a solution. Even if it didn't solve the problem, at least it's a solution. That's just a bad mentality. So the answer would be B. Because D doesn't make sense, C doesn't make sense, and A doesn't make sense. Are we good on 10?
Yeah.
Sandy?
Yeah, we are.
Okay. I'm just confirming with everyone to make sure. Okay, 11.
That's really good.
Suppose that we design a program that appears to successfully solve a problem. Can we skip analysis and jump straight to justification? A is yes, analysis only supports design, and design only supports justification. B, yes, this is what we already do for homework in classes.
Okay.
C, no, the program needs more testing to check its apparent successfulness. D, no, we wouldn't be clear on what makes a good solution. So, A, analysis only supports design, design only supports justification. That's false, because, while analysis defines every metric that we need to follow and every measurable, what we need to measure and what our algorithm should be solving, or design should be solving. Just because it looks like it appears successful does not mean it actually solves our problem. Therefore, A is just wrong. B, don't call us out. C, the program needs more testing to check its apparent successfulness. That's a fair argument. I mean, just because it appears to be successful doesn't mean it works for all cases. D, we wouldn't be clear on what makes a good solution. Well, that's also a good argument. So I would be between C and D if I were to choose one. But what do you guys think?
I believe I chose D. The program. D? Yeah, it was D. It was D for sure.
What about you, Sandy? What would you pick?
I said D too.
Okay. Yeah, because C, the program needs more testing to check its apparent successfulness. Well, we can't. That's not a reason for us to. Wait, can we skip analysis and jump straight to justification?
I think that's unrelated to the question in some ways.
Yeah. I mean, this may be true sometimes where we do have to do more testing, but that's not the issue. It's that we don't actually know if it solves a problem. So these two both are correct because they're no, but this one is more correct than C. Because D defines our metrics on what to measure our algorithm. C just is like, well, you should probably test it more, which is not really a good way of making sure we solved all the parts of the problem. All right. We good on that?
Yeah.
All right, 12. Consider the following problem statement. Find every pair of students in a text file that share the first name. Give two reasonable assumptions that would be useful for solving this problem. If needed, you may explain why an assumption may be useful or will be useful.
So the student would have a first and last name. The first assumption is that you'd be grabbing the first name, their first name. That's one. And I think that's one assumption. And the second assumption is you can solve it either unsorted or sorted, but I don't think that matters too much.
I would say a good assumption to make is that this text file contains students' first and last name, or at very least, their first name. We can assume that. And we can assume that a student is not on that list more than one time. That would be a reasonable assumption, right?
Yeah.
We can probably reasonably assume that it is in some form of list or array based, or it could be represented in some kind of array because a text file has a fixed size, and it wouldn't really make sense for a text file to have pointers. It makes sense just to have probably some names separated by comma or separated by some pattern. Not that the name points to a specific location on the page that then you can grab their name from. That just doesn't make sense. So we can assume that it is some kind of array-based structure for the text file. We should also be able to assume that every pair. But yeah, but I think that's more than. Oh yeah, if needed, you may explain why an assumption would be useful. It's useful to assume that it's an array-based structure because it helps us to define an algorithm for using an array. The assumption about the no duplicates thing helps us figure out that there is we don't have to remove duplicates from the file, and we don't know if somebody has the same first and last name or same first name, or if it's the same person, right? We can't tell somebody's first name apart from themselves, if that makes sense. Like if we have two people with the same first name, how is that different than one person put in the file twice? That's my assumptions.
Mm-hmm.
What do you guys think?
Okay.
What would your guys' assumptions be?
For mine, I initially think that every student in the list would have a first and last name, and
Okay.
you would be you'd be assuming that can be comparing their first name. So let's say John, Adrian, Chad,
Mhm.
Chad. And so I think those are my two assumptions. And I don't know. I kind of want to throw this down. It can either be sorted or unsorted.
Okay. Why do you say that?
But
where did that assumption come from?
Well, because I'm assuming like it doesn't really matter.
Sorted or unsorted, if
It's
you're
either organized or isn't.
yeah, it's like saying, well, it could be everything or it could be nothing.
Maybe that's too
Yeah.
ambiguous or some way. Yeah.
It's not really an assumption. It's just like a vague statement you could say
Yeah.
that is true. It can be both sorted or not sorted, but we can't tell that from the problem description. Therefore, it's not safe to say that there's any sorting to it. Another thing that might be something that we have a bad habit just because of our culture is that they have a last name. Technically,
Yeah.
we're only told that they have first names. Therefore, we can only assume that there is a first name sorting system, or not sorting system, a first name in the text file. It could just be a text file of only first names, or it could be with last names, or it could be with middle and last names, or it could be middle, last names, date of birth, social security number. We don't know. All we know is that there's first names in there. So we should only be looking for or assuming things about the first name.
Yeah, but if we're going to assume something, like the last name is helpful because it kind of gives order to like whether or not the same person is on the list twice or not.
Well, that's one thing. If your assumption then was that there could be duplicates, that's an assumption you just made indirectly. Which how would you back up that assumption? Because if you were to look at this problem, find every pair of students in text file that share the first name, where would you get there must be duplicates or there may be duplicates? There isn't, right? There's no place where we'd see, find every first name of students within that share the same classes that I don't know. If they said like the text file may contain duplicates or something, or if there's anything that could hint towards there being a duplicate, then we might be able to make that assumption. But for the sake of what data we're given, first name, a first name is usually only going to be like a fixed. It's going to be there's going to be a space before it and after it to designate that it's a first name, because it's essentially like a word, and that's what a word is. Or maybe a comma or something separating the letters from non-letters. If we were to assume there's with just that information alone, how do you tell the difference between a duplicate and somebody else with the same first name? Because if you have a text file of all your classmates, and they're only put in there once, and two people share the same name, how is that different than if you were to put them twice? Right? There's no way to tell. There's no way to tell if they're just put in there twice or if there is just two people with the same first name. So we assume, based on what we're given, aka a text file of every student, that they didn't accidentally place a student twice. That's a safe assumption. We essentially assume that they didn't mess up somewhere else. I would argue that's a very safe assumption. I don't know about you.
Okay.
Yeah. Okay.
And if we assume it, or if we reasonably assume that it's safe, then we can reasonably make assumptions from that. Although we've already technically made two assumptions at this point. We've assumed that it only has first names, and we've assumed that it doesn't have duplicates, because it would become confusing and it would infer that somebody messed up. And we'd already answered the problem just by those two things.
Yeah. Okay.
Also, sorry if I seem like I don't mean to seem like
No,
you're good.
No, we appreciate you like really going in thoroughly.
Are we good for 12 then?
Yeah, we're good.
Okay.
So the next one's a pseudocode, and I feel like I'm more likely to mess up on the pseudocode part.
Fair.
But let's see. So what usually helps me with pseudocode is just drawing out the picture of what it might look like, in a way.
Okay, so let's first read
So
the problem.
yeah.
Implement a method, so it's a function, which we are given here, to find, the keyword find, the kth, actually let me snipping tool this. So implement a method to find the kth largest element in array of size n using a minimum priority PQ. Min PQ. Assume that min PQ class has a constructor that takes a single integer, representing its maximum size, an insert method, a min method, a del min method, is mg method, and a size method. Min PQ does not resize. That's a good thing. Does not resize to preserve log n performance. You may not import any packages. Oh, we weren't gonna, I would assume. Creating additional helper methods is fine. So, additional helper methods is fine. Yeah. But you should provide a one-line comment that indicates their purpose. Okay. So given this explanation, we have min PQ, so we should also mark that it's O log n. What we have to work, oh. Wait. Oh, I see.
So I think what we can start doing is drawing out what might look like on a tree. Right? Because so the minimum priority queue would be the most least significant figure at the top, wouldn't it?
Well, we have a min PQ class. Our objective is to find the largest element in an array. Wait, the
Or would
kth
be
largest element? Using a minimum Q. So we have to use a minimum PQ. So we assume that we can take okay.
because it's not saying anything about a max if it's representing as a max heap
It's not a max
in a
heap,
way.
it's a min heap.
So
It's a min
so
heap, and we're trying to find the largest element, and we can remove the minimum. So
the minimum would be the very parent class then, the very at the top, and then let me just. And so the most significant figure would be at the right, and the least significant figure would be at the left, right? Would it still, or can you do it vice versa?
oh wait, find kth largest. That just means like if you have a sorted list and you want to go like find the fifth largest element in a list, which means you normally, if you had a max heap, you'd be deleting 5. You'd go 5 to the past the max, or remove 5 elements from the max, and you have your answer. With a min heap, you'd have the size minus k. Does that make sense? Like, if you have 10 elements and you want the fifth, whether you want to get, whether you're using a max heap, you'd have to remove 5 of the maximums so that you get the kth element, the 5 largest. Or if you're using a min heap, you'd remove 5 of the the smallest. So essentially, in this case, let's say our element is right here. Let me change colors. Let's say we're trying to get 30. K in this instance is going to be 6, right? And let's ignore the actual numbers because this isn't technically a max heap, I don't think. Maybe it is. This might, or it's not a min heap, but if we want to find, oh wait, oh, yeah, okay, I just thought of it. Yeah, so let's say this is gonna be the smallest, right? Let's say this is smallest. That means the thing at the end is gonna be the largest, right?
Mhm.
Normally, in a max heap, all you do to get to here is remove the maximum. So you remove this, remove this, remove this, until you get to this value, right? Until you get until minimum is the value we're looking for. Does that make sense?
No minimum value. So, are you trying to get the least significant value, or are you trying to get in that priority queue then? So like the smallest number. So 3 is the smallest number. Are you trying to get 3 or?
So if this is k largest, let's say, let's actually look at what is the largest thing here. So 100, 75, 50. Let's say k is 3. Our k value is 3, which means we need to find the third largest thing on here. This is the first largest. This is the second. This is the third. So 50 is our third largest. So since 50 is our third largest, and this is a max heap, what we do is we'd remove 2 of the maximum values to get the third, right? I mean, that just makes sense. If you have a list of largest and smallest, you remove this one, and bam, you have the third largest. Right?
Yeah.
But we have a minimum heap, so it's kind of like backwards. So instead, we kind of have 3, 10, 25, 30, 40, 50, 51, 75, 100. And if we wanted to get the third largest, we can't just go and delete these 2 like before, because if we delete the front ones at the front, we end up with something that's like, if we just remove 2 pieces, we end up with 25, which is not the third largest. So instead, in order to get to here, where is it? In order to get to here,
You have the pointer start at the last position of the index.
Yes, except for we're not able to do that because we have to use min PQ. So instead of going k minus 1, so this is k minus 1, to get to the element, we'd have to do n minus k to get there. So if we have 1, 2, 3,
So
4,
n
5,
is the
6.
length of the element, and then you subtract it by k.
So 9 minus 3 gives you 6, and then minus 1 gives you 5. So you end up with x over this, 1, 2, 3, 4, actually I think it was 6. You don't subtract off 1. Does that kind of make sense?
So k is the largest element that you're trying to pick out. So say 3, and n is the length of the array, or the length of the array.
Yes, which is 9.
Okay, and from the top, it's k minus 1 because k is the greatest.
Because this is a max heap, and we have
Yeah.
del max. If we want to get the third max, we just remove the first 2. But if it's the minimum, we have to remove all the minimum values until we get to the max. Does that make sense?
Yeah, I get the bottom one, the n minus k. I'm just trying to see how k minus 1 works.
So
like
if you wanted to get the first largest one, what'd you do? What would you do?
the first largest,
In a
that would
maximum.
be just picking out the parent class of 100.
It would be, let's say you have max del min or del max insert is empty size. So essentially you have max and del max. How would you get the first largest value? Which of those methods
first
you use? Or how many? Yeah. If you have
I would probably try to use delete max then.
delete max, and delete max
Yeah.
would return what?
And that would return 100,
Yeah.
the most significant value.
In this instance, I don't think you call it delete max, but you are getting the max, which is the current maximum. So if you want to just, because max will give you what's currently maximum, del max will remove it and make the next maximum pop up. So you'd be doing max, the normal max method, to get the max.
Oh, so max gives the okay, yeah.
And then what about the second largest?
The second largest, you would call delete. Well, you would call max plus 2.
You delete the maximum value, so delete
Yeah.
100. And then what you're left with is now the maximum is 75, which is the second largest. So you just call max.
Okay, so you delete it and then you call it again. Okay.
Mm-hmm. But what about the third?
The third, you just delete it and then you call the max again. Okay. Yeah. And it just goes, okay.
So this equals, let's say this is number of del max calls. And then after that, you return max. Now for here, you're saying n minus k equals the number of del mins to call, and then you return min. Does that make sense?
Mm-hmm. Can you make it bigger? I just want to take a picture. Thanks.
Yep. And ignore the fact that 51 and 50 are opposite places.
Create new PQ. So looking at how the code might look like, I'm thinking you create a new priority queue, and then you put all those elements inside that priority queue. Yeah.
So.
Or actually, maybe call it the array. So then.
So what's our first order of business?
I'd say you want to create a new priority queue.
Okay.
That represents, yeah.
I'll call it equal. Let's just call it Q. New min PQ, and then how big are we? Wait, what is it?
We can call it data.length.
Well, what? Oh, data.length.
Can you just, yeah, data.length. That would be the length of the priority queue, is what I'm thinking. Yeah.
And now what? What next?
So min PQ, let me just, is equal to min PQ.
We have a.
Yeah, so you call the length of it data.length. So now, since you have the length of it, I think now you want to be able to, I believe you want to loop it in some way. So while, or yeah, you can call it for loop. So the for loop, and I think your for loop would want to start at the first position, so I equals 1.
1 or 0? Remember, you're dealing with Java and arrays. So what is the first position?
The first position would be 1. So then.
You think it's 1? So.
Or wait.
It's the first index, right?
Yeah, it would be the first index because the priority queue does not take up any value in the 0 index.
But this is not a priority queue.
Oh wait, no, it's the data.
Yeah. Are we looping? What are we looping through? Are we looping through min PQ? Because min PQ, we don't have anything to do with indexes.
Oh wait, no. Okay, no, we're going through the data.
Yeah, exactly. Then I is what?
So I is less than or equal to the data dot length.
Now, I do want to point out equal to.
Actually, no, not equal to.
What would equal? If I put less than or equal to here, and assuming the rest of the logic happens, what would be wrong with this? What would happen
It'd
once we
be
reach the last?
getting the exact data versus the less than would be that one off the data. I'm not sure that made. Yeah.
If I is equal to 5 and we have an array length of 5, is there a problem with me doing data bracket I? What happens when I equals data.length? We get an array out of bounds exception. Because an array of length n has indexes from 0 to n minus 1, meaning that n is not a valid index. Only n minus 1 and less than that to all the way to 0. 0 is a valid index, 1 is a valid index, 2, 3, 4, all the way to n minus 1. Let's say 5. So 5 minus 1 is 4. 4 is a valid index. But if we try to use 5, that would throw an array out of bounds exception. So we can't use less than or equal to when we're looping through arrays, unless we start at like 1 and we do this and we do that.
Okay, that just makes it more complicated then.
Yeah, exactly.
So yeah, okay.
So it's a lot easier to just go like this. Okay, and then what else? What's here?
So, I think before you start doing that, you want to delete.
What?
Actually,
we have an empty minimum priority queue. So here, create a new minimum PQ with that can hold data.length number of items. That is what that statement is doing.
okay. Oh wait, no, you don't want to delete. You wanna put all the data into that priority queue.
Yeah, for every element in data. So I plus plus that's what this for loop is doing. Q dot get element at location. So we can go int data. Right. And queue the data into PQ, right? Now, at this point, min PQ contains all the elements of data in min sorted data sorted in min or at least erased. Okay. Does this make sense?
Yeah. So first, what you're basically just doing is putting all the elements into the priority queue. So you're just filling it up.
Yeah. So now
Yeah.
we have this essentially. We have this data structure now set up. Now what do we need to do?
So now this is where the comparison starts happening. No, not the comparisons, but this is where the deletion starts happening.
Okay.
So then, I think first we can initially grab the length of the array. So, yeah, so the length of it.
And here, let's move this up here. Grab length of array, and let's call this instead of int n, equals data.length, just because that's how we're used to seeing it.
Yeah. Oh, so now ends are data. Yeah.
N. Okay. Now.
Okay.
Now what?
So now, since we have the length of the array, I think now we can call n minus k.
N minus
Yeah.
k.
Yeah. So then that has
Okay.
that is, but and I think you can set that as like an int n, or
Whoa.
God, I'm confusing myself right now.
What does this number represent?
That would represent the values from, so n.
This is indexes. So we have an index
Yeah.
of n minus the index k.
Yeah.
So it's something to do with indexes. So it's not just an actual index. We're not saying, okay, index 6 is something. Is this, actually it could be the index of what? Or it could be what is the index? What is this value? This is probably the index of
Index of n.
largest
Of the nth
element. But would you disagree with this?
No, I think that's good.
Because actually this would be it's plus 1, because 0, 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5, 6, 7. 7 is technically the index of the largest element. You'd also represent this as number of deletions, which is n minus k. And if we have it in terms of number of deletions, all we have to do is delete that many number of elements. Right? So for int I equals 0, I is less than the number of, or I is less than or equal to the number of, not less than or equal to, it's less than the number of deletions, I plus plus. And then we just go p dot delmin. Alternatively, we could do, instead of this, we can go and do, if we're starting at the first index, well, I is less than the index of the nth largest element, we're going to delete the minimum value. Both of these are the same statement, they just, you rewrite them differently, that's all.
Okay. You think you could put copy and paste in the chat? I just want to analyze it a bit more.
Fair.
Yeah. Can you enlarge this screen or enlarge the thing?
Yeah, sorry. Does that make it a lot easier?
Yeah.
Actually, Notepad plus plus.
I should probably save it in my, okay.
Study. There. Does that make it easier to read as well? Or is it harder?
No, that's good.
Okay.
Yeah.
Syntax highlighting helps a little bit.
Yeah. Okay, so
for every element, starting from the minimum, delete every minimum until we reach the kth largest element as the minimum. I don't know if that makes sense at all. Essentially, current. We're essentially deleting every minimum value until our minimum value is just the nth largest term. If that makes any sense. And then eventually we just that. Assuming you choose one of these, which one do we like better?
I was gonna go with the n minus k.
Okay. Cool.
K more.
It does. Yeah, that one feels more simple.
Okay. And there we go. Turn the n to the kth largest term.
Okay. And then you return, yeah.
So I feel like what about if it's max? Because I feel like because he's putting min, maybe like the programming would be like max.
So
I think with this, so it'd almost be the same where you just fill up the priority queue, but then instead of n minus k plus 1, wouldn't that just be k minus 1, right? Or was it k plus 1?
I think it was k minus.
I think it was
n minus 1.
Yeah, so the opposite would have been just k minus 1.
Well, actually, in this instance,
Okay.
If we're trying to find the max.
Yeah. Yeah. Del max.
And then
Okay.
instead, yeah.
Delete k minus 1 largest terms. That's essentially what this is doing. So delete the four largest terms in order to get to the fifth largest term. Are we cool on that?
Yeah.
Awesome. Oh. Welcome back.
Okay. I feel like the pseudocode. I feel like he's gonna have us do priority queues for the exam.
Are you guys confident in doing this on the exam?
Yeah, I think it should be good.
Okay.
Yeah.
Pseudocode is always on the exams because that's like the best way to really judge if somebody understands programming algorithms.
Yeah.
So, sorry, because like my computer kind of froze a bit towards the end, but when it's max, is it only k minus 1, like that's kind of being changed along with like the max instead of mins for the PQs?
Yeah. Essentially, k minus 1 is changing. So like if we see the difference between these, they're functionally identical.
Yeah.
All you change is min with max, or replace the words min with max, and you change n minus k to k minus 1.
Do you mind posting this on in the chat too?
Yeah, of course.
Appreciate it. I feel like this he's going to do like max since he like kind of put an example of min on here.
I figured using min is a good twist. Because max is...
Yeah, because we haven't really done min.
Yeah.
That often.
Okay. You good on that?
Yeah.
Extra questions. These are previous practice exams. They are not part of the They're not part of the practice exam, may not use content not covered in the current semester, but are provided for additional practice. Which of the following ways would insertion sort process the fastest? A, B, or C? So it's insertion sort. And we have an array that is in sorted order. We have an array in kind of sorted order. And we have an array in reverse sorted order. So, and we have D, they will process the same speed. What do you guys think?
I think it's 1.
You think it's A? Sandy?
Yeah.
Mm.
Yeah, A.
A as well? Yeah. A is it. We talked about this earlier. Sorted order insertion is the fastest. Consider the following array: 23, 7, 35, 3, 4, 2, 13, 1. Show a trace of execution for top-down merge sort. Illustrate how the array is broken down, then merged into an ordered state. So, let me see if you can see this. Is that all of them? 13, 23, 7, 35, 3, 4, 2, 13, 1. Okay. So, move this space. Okay. What would be step 1? What would step 1 look like? And I think he has these kind of questions on the quiz.
So for, let's see, merge sort, you're breaking it down so it'd still be the same. So you cut it in half.
Okay. Then what about step 2?
The same.
It'd be the same up till you reach to the midpoint. And so the midpoint of it would be at, I'd say, so 1, 2, 3, 4, 5, 6, 7, 8. So between 1, 2, 3, 4. So 23 to 3. Cut it down again, 23 to 7. Cut it down again. So now at 2, 2 would be the midpoint of it. And so after 2, that's when it starts merging together. So you're comparing 23 and 7. 23 is less than 7. So then you swap that. And then you're comparing 35 to 3. 35 is greater than 3. So you swap that. And then 4 and 2. 4 is less than 2. That gets swapped. And then 13 and 1. Yeah, 13 is greater than 1. That gets swapped. And see, and then you compare those two. So the first two index, so 7 to 23 to 3 and 35. Those two are being compared. And so those get in ordered.
23 and 35.
Yeah, and then the second, and then the next part would be 2, 4, 1, and 3. So 2, 4 is being compared to 1 and 3. So then it'd be 1, 2, 4, and 13. Yeah, not 3, 13, I mean.
Okay.
And then from there on, you're comparing those 4 values to the 4 values to the next 4 values up front. And that is when it's in order.
Like that?
Yep.
Yeah. I can't remember if, I'm pretty sure if this were an exam, some of these steps would be done at the same time because of the divide and conquer. So when you're ordering 23,
Yeah.
7 and 23, you'd end up with,
It'd be on the same step as, yeah, I know what you mean.
yeah, so I want to do that as if it is in the same step. Then what do we do? 6. This is order, that side's ordered. Right. be this, I think. Yeah, because here you're sorting this, so we haven't touched the array yet, but here we're sorting this one and this one. Then we're sorting this one and this one. Then we're sorting this one and this one. And then we put them all back into place. Okay. Does that look good?
Yeah.
Okay.
You get Sandy?
I usually kind of like to draw out lines to like kind of.
Fair. You can kind of here.
Yeah, that's good.
And here it becomes essentially, does that kind of look right? Where the divisor is between the two different processes. One process sorts this, another process sorts that. Same with here.
Yeah.
Okay. Okay. We're good on 2. Short answer 3. Sorry if the questions have been hard to read. As mentioned in class, a max heap would be a great data structure when we need to extract the maximum element. Let us say that you are given a few processes that require CPU time, which are stored in a heap structure. The process with minimum priority needs to be executed first. Example, a process with priority 0 needs to be picked up before a process with priority 1. We need to select the task with a minimum priority. What would be the time complexity to simply read the minimum element in a min heap?
That would be 1 times, wouldn't it?
Sandy?
I think so. Yeah, it would be 1 times.
I agree.
You agree? Okay. Yeah, it would be 1. Because stored in a minimum priority heap, assuming we have already done the sorting process, it is 1. However, to get the maximum, we would have to
That would be
O of n. Actually, n log n.
And log in?
Because every time you remove an element, you have to resort, which is log of n. So
Okay.
for the
Yeah.
number of elements you have, n, times the amount of times you have to sort, log n. So you get n log n. Okay, I think that's it.
Yeah.
Cool. Any other questions? Or any other things in general?
Can we go over the midterm exam too, or?
Sure. Midterm.
Midterm.
Is there a midterm?
Yeah, like he had an example under the exam 2, like the old exam.
Old exams?
Exam 2.
This one?
Do you mind if we go over these two?
Sure. This is exam 1.pdf, exam 1.pdf. I don't know why.
Is he? I don't think he's going to ask us any questions on the induction proofing, is he?
No, that would be previous chapter.
Yeah. I think all these questions look to be just asking about a big O.
This does have elementary sorts. This seems like exam 2.
Data abstraction, bags, tags, queues, analysis. Oh yeah.
If you're given an interface for an ADT but no actual source file, how well can you run a program against it? Hint, there is a type of method that cannot be specified in an interface.
So maybe like
Is this the thing you want to go over?
Yeah.
Well, can you program against it? But not actual. Oh, isn't that generics for the hint? There is a type of method. Oh wait, no, that's not. That's not. Generics isn't a method.
I would assume an abstract method. You can't, for an interface in Java, you can't have fields, but a field can be represented in a method, so that doesn't really count. Abstract is something you can't do in an interface, but you can do in an abstract class. I don't know what types of methods can't be. What? I would assume abstract. But an interface by default is an abstract method, so I don't know what he's getting at. ADT.
Just too far enough. Now is it important to know? I don't think he's going to be asking us any questions about anything from our last modules, from test 1.
That would be extra stuff. Yeah.
Yeah.
It's the same as is different.
But any questions on sorting, analysis, and algorithms? The big O, we should show the upper type of F. The upper bound you gave F1 above does indeed hold.
Which one did you want to look at?
We can try looking at big O analysis of algorithms for 3.
Oh, this one? Or no,
yeah.
Just give me a problem.
Oh yeah, problem 6.
Okay. What are the big O orders of the following growth functions? You should provide a relatively tight upper bound.
A tight upper bound. So then the upper bound of the graph being worst case? Yeah. So show the upper bound. So that would be, wouldn't that be 45n? Or O of n?
It's asking for the order.
Oh, the order?
Yeah. Big O orders of the following growth. Oh wait, yeah. What is the big O notation of F1, and what's the big O notation of F2?
So then for F1 that would be 45n, or oh no, big O would be n. Yeah.
Not necessarily, because this isn't the
Really?
fastest growing
Isn't
element.
Or actually no, n squared. Not 45n. Would it be n squared? It's
It'd
actually
be n squared log base 10 to the negative. What was that?
Oh, I agree with you. It should be like the middle one, minus the
Oh.
10.
Yeah, without the 10.
Oh, yeah. Damn.
This is smaller than this, so we ignore it.
Yeah.
This is also smaller,
Yeah.
so we ignore it. And here, what about F2?
Where?
Which is larger?
Ooh, the bases are different. I want to
Log
say
2?
You think log 2? Okay.
Actually, I'm not sure. Like, I've encountered this. It's like,
I remember yeah, I remember looking at this. It was like the bases were different, but one of them, yeah, I can't remember which one I chose.
So here, let's just graph it. Log base 10 of x, log base 2 of x. Which is bigger?
Oh, it was log base
2.
2. So log base 2 would be the okay.
And if that is x log x, but I'll put it like this. You'll see.
Yeah.
It's still the same thing.
Okay.
So it'd be O of n log base 2 of n. And then the order of them is... Oh, yeah, we just need the big O. Okay, show that the upper bound...
If you were to ask about the order, the growth order, what would, like, does that mean, like, he wants it in, like, some order of, like, the most worst case to least worst case? Like, the best case?
Yeah. I would assume, like, he would say order the big O orders. Like, order
big
F1
O order
and F2 in terms of big O.
In terms of big O. So it would be from the worst case to the best case.
Yeah.
Okay, and the worst case being, I believe it was n square log a tendon, and the best case being, I believe,
F2, right?
What?
I would mean like big O of F1 and big O of F2. Which one is larger? Specifically.
Which one would be larger?
Yeah.
Okay, so then the larger one would be F1.
Yes.
Okay.
It's n squared, specifically.
Yeah.
Log of any constant really, times n is going to be smaller than log of anything of n times n squared. If that makes sense.
Yeah.
Just because, like, you look at it, x log base 10 of x. If this is x squared, its magnitude's larger.
Yeah.
Okay.
Okay. Yeah.
Show that the upper bound you give for F1 above does indeed hold.
So a quick question: when it's if it was asking for a relatively tight lower bound, are we still looking for the largest for both? Or we're looking for
relatively tight
lower.
Wouldn't that be like tilde then?
Tilde?
Lower.
Or lower bound.
I think it's maybe. I'm trying to think of tight bounding and how what that means in actuality. Because I know it's like the upper bounding just means like if you have a function that is that encapsulate the maximum values of it, and lower bounding is like minimum.
Because when it comes to looking at big O, I always assume we're looking for like the largest in like whatever equation, like, and then drop the constant.
Yeah, and that is correct.
Well, I don't really think of it in terms of like tight upper bound and lower.
I don't either, and I don't think most people do. I just think,
Okay.
um,
I was just wondering if it changes, if it's like if he's asking for like a relatively tight lower bound.
I think the lower bound would be n log 10. Because when I think of upper bound versus lower bound, upper bound usually means like something that goes from like here and kind of bounds between here, and something that goes
Yeah.
and so if it would be lower bound, I would assume would be the purple because, well,
Mhm.
yeah, I would assume the purple because comparing two of the largest growing functions, this one grows lower or grows less as
Yeah.
much than this one, but that wouldn't really make sense. I don't really see why he would ever ask us the lower bound rather than the tight upper bound. Because if it's big O notation, you want worst case. And yeah. I don't know. I would assume yeah.
Okay. I just was wondering, just like in case.
You know, it's a valid question. I just don't know. I don't know the answer to it really. I don't really know why you'd ask that or why he'd ask that.
Okay.
Because if I knew why he'd ask that, I'd know an example, but I don't know an example. Show the upper bound you give for F1 above does indeed hold. I think that's an induction proof, maybe. I don't
think
know.
maybe you can just point out where the growth is happening at.
Perhaps.
I don't.
I don't. He doesn't really go too much about upper and lower bounding. He really only went a lot on big O and tilde.
Yeah. So maybe like 7 would also be like, because it's logarithmic, it's growing exponentially?
Mm-hmm.
Or I don't know. Okay.
Something like that. Those terms end up being larger than the others. I don't know. Okay. We move on to 8 because those two are a little wordy, or a little strangely worded, and I think they're from. Hopefully, you won't reuse the same question.
You have
We
two
can probably
algorithms,
ask
A.
assume you have two algorithms A and B. A is O of n, and B is O of n squared. Will the algorithm A always run faster than algorithm B on real-world inputs? Explain.
N and N square. I feel like yes. Because if you put any values into N, so 1, 2, 3, 4, 5, that would be just that 5, but then
I see what you're
put any
going
values.
and I want to stop you because I think you're forgetting about one key detail here. Big O notation is an abstraction of the worst case, right? The worst performance.
Okay.
As you scale amounts. And the keyword here is always run faster in real world inputs.
Oh,
Let's
so
say
then
you have if I make an algorithm that's like for 0 to 1,000,000, print hello world. And then I'm like, okay, for I is less than n, system.out to print n, or the data at n. And I was measuring how many times that system.out.print was called. It would be O of n, but the actual function of it, the growth function of it, is n plus 1,000,000. And B, let's assume it's a 2D array or not in 2D array. Let's say it prints every number times every other number. So it's a 4i nope, pad plus plus. Well, actually, notepad. So you have 4 or print values. Let's say we have this. 4i int I equals 0. I is less than array dot length I plus plus. System dot out dot print line. We have this. Let's call this. Well, this is A in our instance. One way of doing A. Also, I'm going to zoom this in. And then we have B, which is we can do let's call this one way of doing B, right? The big O for these, O of n squared, and this is O of n. And we, n is number of print line calls. Now, sorry. What happens if I were to do this? Not this. What is the big O notation of this method?
Say, would that be n squared then?
Why would you say n squared?
Or
Well,
because the extra for loop, but then maybe
but n is a measure of like number of print line calls in respect to data size. So if I have n number of elements, so let's say
oh wait,
5.
no, that would be one of the second part, so it'd be so it'd still be n times, wouldn't it?
Yeah, exactly.
Yeah, okay.
But you can see if I have a 2D array here and has 4 elements in it, and we're taking a real world example, and we print this out, the number of times this is called is 16, right? What about here? This is if this is an array of only 4 elements, then this is going to print out 4 plus 1 million. So it's going to be 1,000,004 operations done with an input of 4. Do you see that how big O can kind of omit other information that we're not being told? It's like even the tilde function of this is approximately n. Same with here. Tilde of approximately n squared. But the actual growth function of it looks something like this. And the growth function of this just looks like n squared. And if we graph these, what was n squared versus f of n equals n plus 1 million, you'll see if we scroll out, and we keep scrolling out, there we have that. So you can see it takes a very long time after about 1,000 elements. If we have a data size of less than 1,000 elements, then our O of n function performs worse in a real world scenario. But if we have something greater than, it starts performing more, or like better, due to the growth. So over the long run, O of n squared performs worse than O of n. However, in a real world situation, if our data is not breaching this threshold, then we may be having a less performant algorithm as a result. Do you guys kind of see what I'm talking about, maybe?
So the further out it goes,
Yeah.
the performance of n isn't greater than n squared, versus the n squared, the performance is not is worse compared to n when it's given a smaller set of data, but then the further it grows versus n, then n squared would be better. This is what I'm getting at?
Yeah.
Sorry,
We
it
can call
was
n
kind of
squared b, and we can call n
yeah.
a. So
Yeah.
a starts out with a ridiculous number of function calls that is not needed for this size of data, right?
Yeah.
And with big O, we don't see that it's doing that. Only with the actual growth function do we see that. And because of this, if n is anything less than 1,000, we have A is more expensive to run than B. Regardless of the fact that it's O of n and O of n squared, it's because the growth function, the actual number of calls being made, is much larger. This A is just larger than B until 1,000. After 1,000, B passes it. And that's why in the big O notation, it's telling us in the long run, if you have a large enough piece of data, B is going to be slower than A. But that doesn't tell us for any size. And it doesn't tell us always. It only tells us in the long run, or with a large enough piece of data, B is going to be larger than A. That's the only information big O and tilde can really tell us. Without the actual growth function, we can't tell whether or not they are larger, if B is larger than A at all times. Does that help? A little more confused? Or do you understand it?
So
So the long run, you said B is worse than A?
In the long run, B is worse than A.
Okay, and then, but in the short run,
Yes.
B is better than A.
Yes, but we don't know that unless we look at the actual either tilde notation or the growth function. The growth function can tell us everything we need to know. But if we don't have that, maybe we have tilde. And if we don't have that, we have big O.
Okay.
So when we want to judge the comparison of algorithms, we want to start with the most accurate information we have to compare two things. If we have two growth functions, we can accurately compare them to see which one will perform better. That, like, undeniably. When they're based on a certain data, we can figure out exactly how many calls are done in a certain time. But if we're comparing tilde notation, we can only compare on average which one grows faster. And with O notation, we can only determine generally which one grows faster. And so if we're comparing big O with tilde, tilde is more accurate, so therefore we want to trust tilde more than big O. If we're comparing big O and growth, we want to trust the growth function because we can see more information. It's Like, for example, if I were to do this, make this 4, this would be 4n, but the big O is still n. So if we have function A, which is O of n, and function B, which is tilde 4n, we still want to trust function B because we know more things about it.
Okay.
Function A could be 1,000,000 n. It could be 1,000 n. Or it could be n. We don't know. We're not given that information. Therefore, we trust the one that we have more information about. That's like how you do the comparison of big O to tilde, big O to growth function to tilde. You want to pick the one you know more about, because if you know more about it, you can figure out which one will perform better for your instance, right? The only difference is if they have different degrees of increments, but I don't know. You got to use your brain for that part. If something is 2 to the n versus n, obviously we want to use the n for most of the part, or for just the fact that it's ridiculously hard to solve, right? It's an exponentially difficult problem to solve. I don't know. Sorry if it was a little confusing, but
Can I see the notepad again enlarged, please?
yeah.
Okay. I got it. Thank you.
I'll post it in the chat just in case.
Thanks.
But yeah. And then on to number 9. What is the big O order of the following code fragment? The fragment is parameterized on the variable n. Assume that you are measuring the number of print line calls. So this is the same similar thing. So essentially we want to measure how many times we call print line. So this statement. So for I equals 1, I is less than 2 to the power of n, I plus plus.
Plus equal. So it's incrementing by 10, right?
This second loop is incrementing
Oh yeah, second
by
loop.
10.
Yeah, but then the first loop is incrementing. It looks like it's to be exponential by 2n. So then that would be
2 to the n, yeah.
Yeah, 2 to the n. I don't think that would be log of n times. So
No, anytime you're
no.
The difference between log.
Oh, isn't that factorial? Yeah.
Not factorial. It is 2 to the n. It is literally just the big O. You can have
2 to the n?
Yeah, you can have some number to the power of n. That is another metric. So if we're talking about big O graphs.
Oh yeah, I forgot about that metric.
You have 2 to the power of n. You have hold on. 2 to the power of n. You have x, or you have x squared times 2 to the x, but you'd also have x to the 4th, x to the 5th, x to the 6th, x squared, x cubed, x log of x. You have if we were to look at the overall here.
Oh, so it'd be 2 to the x then. Okay. Yeah. Okay, I'll be right back.
Yep. So you can see the At some point, 2 to the x will be more than... Hold up.
I think is this answer just...
You can see here, the largest growing terms you have
Oh
is
man,
x squared
I didn't.
times 2x to the x, x times 2 to the x, and then 2 to the x. And then over here you have x to the 6th. And then everything else is so small in comparison that it doesn't even chalk up. So when you go scroll, Tismos doesn't like that.
Damn, I didn't eat anything this morning. I literally woke up as we were about to start this.
Oh, my bad.
Nice first
No, you're
talk.
good. No, you're good. I was like, oh shit, we're about to start. Let me just, yeah.
Fair. So you can see, you got x squared here, and then 2 to the x. You can kind of see how 2 to the
I'm gonna
x
mute myself.
ends up being larger. You see that x log x ends up being larger than just x at some point. And constant is just constant, so it's always going to be the minimum. And then log of x, you end up having pretty almost 1, but not quite 1. You essentially have very close to 1, as close to 1 as you can really get. So, I don't know.
So are you just explaining the order of the growth?
Yeah. And so you
Okay.
can see this is 2 to the n because when I
Yeah.
is less than 2 to the power of n, you end up with the largest growing term to the n. And then inside of there you have n. And do you know why this is O of n and not like O of something else, like n over 10?
Are you saying for the second for loop why it's O of the n?
Mm-hmm.
Is it because n is the length of it, so you're still getting of n times, even though if it's even though it's incrementing by 10, you're still getting of
Yeah.
of n times. Yeah.
Yeah, exactly. It doesn't really matter how much it's incrementing by, as long as it's incrementing linearly, aka addition, then it's O of n. And so you have O of 2 to the n times O of n, so you end up with 2 to the n number of system.out.print lines. Does that make sense?
2 to the n, and then it would just be big O would just be n.
Big O of this entire thing is 2 to the n times n. So
Okay.
there's an actual way you can calculate these, and
Okay.
using Wolfram, he had mentioned this before.
I don't think he's gonna let us use Wolfram on the test.
I get that. I'm just letting you know in case this ever comes up. I
Yeah.
equals 1 to 2 to the power of n times, or then inside of it you have another summation where j equals 1. J is 2n of, what is it? Oh wait, this wouldn't be, oh yeah, we'll just assume this. 1. You end up with the sum of this ends up being 2 to the n times n. See? That's how you like actually do the math behind the big O, or the function.
Okay.
Because if it was like there's 2 function calls inside those for loops, then you'd have a 2 here. And you'd end up with 2 to the power of n plus 1 times n. You see how that math works at all? How you get the equation from this? Right. Are we good on this?
Yeah, we are.
Yep.
Thanks for clarifying. And I feel like this is this like 10 and like what's below is what he wants us to review. Because last time we didn't go over them because we hadn't done it yet.
Yeah, selection sort.
Implement a selection sort.
So consider the following selection sort, which we've seen on his slides. If you were choosing a cost metric, what operation should we be counted in order to determine the algorithm's big O order? What operation would be the best choice? What do you guys think?
That'd be the 2 for loops.
Well, what's the cost metric?
Oh, cost metric? Wouldn't it be of n square, right? And
Cost metric is not like not the big O. It's what.
Aren't you pointing out what piece of the code is running of what time, and then you're just like sticking it together?
You're
right?
trying to attach some piece of code to something you can measure. Essentially, you're making a measurement. So, are you measuring in meters? Are you measuring in seconds? Are you measuring in hours? I mean, in this case, what method are we measuring? What is our unit of measurement for our big O?
So the number of times the exchange is happening then, right?
So you want to measure exchange. So if we want to make a good big O that describes this method, we would be describing a number of exchanges, right?
Yeah.
Okay. So let's run this through. If big O is determined by the number of exchanges, what is the big O of this?
Big O of the first for loop?
Well, big O of exchange calls. Because big O just describes something. You can describe big O as either the amount of memory being created, the amount of system.out.print calls, the amount of exchanges, the amount of comparisons, the amount of subtractions, the amount of additions, multiplications. It can be anything. All you're doing is, okay, given n number of terms, how many times does this cost metric get run or get called?
Oh, then it would be n squared then, right?
At first, you might think for exchange, it would be n squared, but think about the fact that we don't care what's before exchange, because exchange doesn't happen inside of this for loop, this second for loop. It only happens here.
Oh, wait, yeah, no, it's out of the for loop. Yeah,
so
okay.
it ends up being O of n number of exchanges.
Okay, yeah.
But what would be a better cost metric to really summarize this algorithm?
Oh, so it would be that if statement then.
The if statement? You'd say, what about the if statement? What is happening in it?
Because it's comparing whether if j is less than, yeah, just a comparison.
So you'd be measuring comparisons. Do you see what I'm saying?
Yeah, I see it.
And technically, if you wanted to measure, so we'd be comparing the less than function calls. If we wanted to measure comparisons, we'd also be considering this and this, not just less. But for now, let's just choose less, because that makes the most sense. Most of the time, you're not measuring the less than or equal to sign. Okay. So knowing that we're comparing this, we then go, okay, this is O of n, and then times, what is this? This is O of n, so O of n squared. The actual growth function for which, I want to show an example of that Wolfram alpha. So from I equals 0, we're going to go to n, and j equals I plus 1 to n. And then we only have one comparison statement, so it only gets called once. So what is the growth function of this? Here, expanded form. We end up with n squared over 2 plus n over 2, which the big O of that is just n squared. And if you remember back in our slides, we can actually see exactly where that was. If we go to selection sort, selection sort, what do you know? N squared over 2 comparisons and N exchanges. Remember how you made the cost metric the number of exchanges, and then we end up having O of N?
Yeah.
That's represented by this statement from the slides. So you
Okay.
can choose anything to make a cost metric. Like I could choose the number of times we increment I. And that would be N, O of N. How about the number of times we increment J? Well, O of N squared.
Mm.
Does that make sense?
Yeah, okay, I see where you're going with it.
You can essentially just pick and choose what you want to actually measure. If I want to do the number of times you do A dot length, well, 1, O of 1, because you do it once. My method has O of 1, number of checks of the length of the array. But you can see what I'm saying.
Yeah.
Cost metric is usually you want to use the cost metric for something that is costly, the most costly thing. And that's kind of what you want to base your algorithm off of. And in this case, comparisons are the most costly here. Maybe exchanges, but we do more comparisons than exchanges by a larger degree. Okay. What did you want to say?
So the for loops would make it like O(n) squared, but then like because we're looking at the most costly over here, it would be O(n).
Yeah, anything
just like that line.
So int min equals I. This is O of N. Exchange. This is O of N. Int j equals I plus 1. O of N. J less than N, N squared. J plus plus, N squared. If N squared. Although this isn't really called. But less than O of N, or N squared. A brackets J, N squared. A min O N squared. Min equals J, unknown. We can't determine it, but worst case, N squared. Does that make sense?
Yeah.
You can kind of pick whatever you want and use that to measure some big O notation or some growth function. Are we good on 10?
Yeah.
Sandy?
Yeah.
Okay. 11. Embeddable hardware. Oh, actually, do we want to... What questions now? I gotta do other stuff today, so I might wrap this up within like the next 20 minutes if we can.
Can we just go over the sorts and merge sorts?
Okay.
We don't need to do 13 because it's just... Is it just kind of drawing things?
Yeah, we did this.
Drawing it.
It's the merge sort one.
Yeah. So maybe like just 14 and then like 11, 12, 14 I think are good.
Why does a sorted input require fewer comparisons than an unsorted one? Hint. Think about how much you learn from each comparison in both of these cases. So, a lower bound proof, if we were to think of, if we were to draw this out actually, actually, that's why I have a big document. Shapes. We have this decision, and let's say the right path is going to be, so anything on the right is going to be, it is sorted, everything on the left is going to be unsorted. If we have a sorted array, all our decision tree looks like ends up being this, right? We end up just going down the line, and it ends up just being however n many statements, that's the number of comparisons we make, right? But with unsorted data, we have a decision to make. And we could, in theory, go here, and then go here, and then go down here. Like, you can keep going down the rabbit hole until you end up with the sorted answer. And the amount of comparisons needed to be made for a sorted... So, every combination of the array is n factorial, right? And given an array is sorted, all we have to do is confirm that it's assorted, right? In order to quote-unquote sort it. So therefore, you only need to go through every element one time. Until that, like... Because as long as every element you've checked so far has been in order, you have a sorted array. And if you can do that through the entire array, you only have to go through once, and you know it's in order, if that makes sense. Because you're just checking current element, is it greater than the one before it? You keep doing that for the whole entire array, and you know that it's sorted. But if it's unsorted, then you need to decide where it goes. And so, where it goes entirely depends on where it is, and you end up with this n squared, or n factorial decision tree, right? Because there's so many different locations that it could go. It could go at the end, it could go at the front, it could go in the middle, halfway between the middle and the end, somewhere. And so we'd have to figure out exactly where it is. And that's why the decision tree, the lower bound proof of the decision tree of an unsorted array becomes so complicated.
Okay.
Because you have to check every combination for an unsorted array. Does that kind of make sense?
Yes.
So, just one quick question.
Yeah.
So back to selection sort and insertion sort about the runtimes. You talked about how n squared over 4 is the average runtime for insertion sort.
Yes.
What was the average runtime for selection sort again? Was it like...
It's the same as its worst case and best case.
Same as worst case and best case.
Yes.
Okay, and the reason why insertion sort is n squared over 4 being the average time compared to the average time for selection sort, why wouldn't...
Why aren't they the same,
why
is one not better than the other?
Yeah.
Okay. So
comparing the difference between the runtimes between selections and insertions. Because I'm confusing myself with my runtimes. Yeah.
So we have a selection sort right here, right?
Yeah.
Given any ordered data, what is the worst case scenario and best case scenario of the amount of times it has to run? If we're measuring the less than calls.
That would be if it's in that if statement, then that would be n squared times.
Yeah, it'd be n squared. And the tilde notation is n squared over 2, just because we proved that with the actual in Desmos. It's n squared over 2. The actual growth function is n squared over 2 plus n over 2. But that doesn't really... We're not really... we don't care about that part. However, with if we look at the algorithm for insertion sort, let's look at this. We have for I equals 1, I is less than n, so we have one for loop. I don't know if you can see it well. Can you see it?
Yeah, we got it.
Okay. So you essentially have your first for loop, which goes to the entire array minus the first term. So we'll call this n. N number of times it has to go through. And then inside of it, you have another for loop. So it's going to be n squared something, because it's not exponentially growing, it's linear. You can see j minus minus. But j starts at I. So on average, it starts wherever we're currently looking. So on average, it'll be about the middle. And while j is greater than 0 and the value at j is less than the value at the one behind it, we're going to exchange them.
Mhm.
So we saw that in the visualization here, we saw that insertion sort kind of makes an ordered, anytime it reaches something unordered, like for instance that really small, you can see like all these pieces are at various heights, right? There's a random sort of
Yeah.
data. Every time it goes to the next element, it takes that element and puts it in the sorted place on the left side. So therefore it doesn't have to touch that piece of data anymore. And if you repeat this process and just shift everything that if you keep sorting, if you have a stack of papers and you take the thing off the top and you put it into a sorted stack, and you repeated this, and every time you placed it in the sorted stack, you placed it in where it's supposed to go, you end up not having to, on average, I'm trying to think. There is optimization here, essentially, because as you're going through the array, you are looking throughout the entire array and trying to find where it is supposed to go. And once it's found where it's supposed to go, it stops and goes to the next element. So the actual sorting part of this algorithm is not n. It is not n every single time, because, for example, when it's going through a perfectly sorted array, it knows it's already sorted, therefore it doesn't have to move it at all. Therefore, all it is doing is going through the entire array and checking that things are sorted.
Mm,
Does that
okay.
kind of make sense? Maybe?
So the best case is of n times, right? And the worst case is n squared.
Yes.
Okay.
And then the actual tilde approximation, if you were to average this out for a random set of data, ends up being n squared over 4. So we can
And that's okay. And that's from using Wolfram Alpha in is what you said?
This would be
Or
a
is that
lot
just from
more difficult to do in Wolfram because you don't have conditionals.
Oh
So
yeah.
it's not necessarily going to, so like normally
But
you have
okay.
from 0 to n, I plus 1 to n. Here it would be to sorted position. Does that make sense?
Okay. Yeah. So to tell that it's like, how do you know if it's 4? Like it could be 5, 6, or like, how do you know it's being what number is being divided it to? Like, is it divided to 2, 3, 4? Like,
So
how
if you
how do you pick?
so let's say you visualize this, right?
Yeah.
If you're halfway through sorting, right here, and you were to give me a random number between those heights, on average, where should it go?
To the middle.
To the middle, right? And so you're at halfway, and the middle of halfway is 1/4, right? Therefore, 1/4 is where we get that. That's where the 4 comes from. Because on average, elements only have to move half the array, half the sorted
Oh.
section, and half the sorted section is at halfway is 1/4 of it. So you're averaging an average, if that makes sense.
Okay. And that's where utility comes in.
That's the tilde part of it. It's a generalization because the worst case is n squared. Best case is n squared over, it's just n. So somewhere in between there, you have n, on average, n squared over 4.
Okay.
So actually, we could probably look at this. It says 1,024 numbers. Let's see. If we take out our calculators, if we go 1,024 to the power of 2 divided by 4. We should guesstimate about 262,000 writes to the main array and comparisons. Bam. 265, which we're off about 3,000, which is a really good percent error. That's very close to what actually happened. Do you kind of see?
Yeah.
Yeah, that's how you can use tilde to actually see if you're generally on or off, right? With merge sort, you can actually calculate how many or not merge sort, sorry. How was it? Not bubble sort, selection sort. So we have 1,024 numbers. 1,024 squared is this number. Divide that by 2. We should have exactly 524,288 writes to the array. We'll see that. Or comparisons of them. Or we should have, yeah. Dang it. But you can see what I'm saying. It is very close to that amount.
Okay, yeah.
500. Yeah. Because merge sort is always, no matter how many amounts is... No, not always. It's generally that. Anyways, you see what I'm saying?
So, selection is better than insertion sort?
No.
No.
So, this is... Insertion is n squared over 4. Selection is n squared over 2.
Okay, so insertion is better at the best, at the average case. Okay.
It's better at average in comparisons. It's better at... it's equal to reverse for selection in comparisons. It is better by a factor of n, so it's a lot better with when it is sorted already. The exchanges, it is worse on average. For the exchanges, it is worse for the worst case. It is better in its best case, because we're comparing this to n and n squared over 2. Does that kind of make sense?
Yeah.
Sorry, that's a lot of comparison stuff.
Yeah.
And that's for insertion, right?
Yes, this is for insertion.
Which one was for selection? Selection was... I think for selection it was...
It's always this.
It's always n squared over 2. So can we go over 11 and 12 for the midterm one? And then I think we should be good, because like the rest is just review. And like the big O stuff he gives, extra questions, is just like big O from last time.
Alright. So embedded hardware with solid state has a limited number of writes during its life cycle. Limited number of writes means we want to optimize exchanges. Hence, one sorting algorithm design goal is to minimize the number of writes that are made. Of the sorting algorithms discussed, which achieves that goal, even in worst case? So we have...
Worst case?
We have insertion, we have shell, we have selection, and we have...
Merge sort?
Merge, yes.
So I think between shell sort and merge sort, I believe...
We have a limited number of writes.
So limited number.
So that writes
involves
swapping, it involves creating new arrays, it involves anything.
Oh, okay, never mind.
Like writing data to the array, not just reading it.
Oh, so basically, it's limiting.
So is merge sort good for this? Let's start out with that.
I don't think so.
No, because it has to create new arrays, and each time it does, it has to write things, and it's not just swapping elements, it also needs to create copies of the array. So let's throw that out of the window. What about a
Shell sort?
yeah, what about shell sort?
Hmm.
No.
No, why? Actually, let's go to insertion, then we'll go back to shell, because shell uses insertion.
Okay.
So insertion sort, what about that one?
With insertion sort, you're just comparing what's in front of it and then just putting it into the exact spot. Well, you're just putting that
Not
number
necessarily.
into.
You have to swap every element until you get it into its proper position. Unless it's a linked list-based insertion sort, which is probably not the case, you have to swap every element from the current position to where it's supposed to go. Because think about it like an array. You have to shift the elements.
Mm, okay.
So we will say iffy on the insertion and shell. What about selection? What is the worst case for selection in terms of rights and exchanges?
Worst case is that it would be flipped though, wouldn't it?
Worst case for selection specifically, it has the
And
same.
it had to grab the. It has to like move. It has to grab the very end of the nut. Yeah, the very end, and has to move it to the position of where it needs to be, right?
This is selection
Or am I
sort.
describing?
We have our tilde for it is n squared over 2 for comparisons, but for exchanges we have n, right? Now.
Oh wait.
And we're looking at exchanges.
Ah.
So is selection a good algorithm or a bad one for this?
And I'm trying if I can remember insert. I think it'd be good. Yeah, because of n times. Yeah.
So we're told to look at worst case scenario. Worst case for insertion is n squared over 2. Shell sort probably also something similar because it uses insertion. So, and then, so insertion sort and shell sort are worse than selection sort in this instance. And we already ruled out merge sort, therefore selection sort is the best.
Yeah.
So our answer would end up being selection sort because it.
So you're just comparing the two worst cases together, and whatever it has like, whatever is the best worst case, then you're just picking with that.
Yeah, you can see that by
Okay.
of the sorting algorithms discussed, which achieves that goal even in worst case.
Oh, okay. And so then, for worst case, it would be the selection sort. Okay.
Yeah, because worst case, it is still only n, which is great. Because everything else, it's much higher than that. Magnitude's higher than that. Okay. Are we good on 11, or are we still confused?
No, I'm good.
In terms of sorting quickly, would we ever want to use insertion sort instead of merge sort?
Sorry, would we ever want to use insertion sort? Would we ever want to use insertion sort? I think merge. I would say no.
What do you think? Sandy. What do you think?
Well, I was thinking, yes, do you want to use insertion sort?
I picked no because merge sort is n log n times, and n log n is quicker than n square. But I don't know. Maybe that's just too simple.
No, at first I would I think I would do that. I think there's very rare edge cases, like if you don't have, like, no, I think this would be correct. Like, there would be no reason if we're only caring about speed that we'd want to do n squared versus n log n. Because if we graph this, and we take off this, n squared versus n log n, n log n just beats it easily.
Yeah. Okay.
Like, there's not even like a comparison between the two. The only, I guess, the only caveat
so
maybe
merge
is if it
sort.
was like plus 50 or plus 500, but we're not comparing growth functions, we're comparing O of n. So maybe I would put no unless insertion, or unless merge sort had some other kind of overhead that took longer or something. I don't know. I would choose merge sort over insertion sort though, based on the information we're given.
Okay.
Does that make sense?
Okay. So, are we good on things here? I think I should be good on everything.
Okay.
Yeah.
What about you?
Yeah. You said. Well, I feel much better about it, but can I also get the link to your recording so I can go over things again?
Yeah, I'll send you the YouTube.
Oh yeah, yeah. Yeah,
And
send
then
me that too.
yeah, I feel like if I watch this again, then I feel like I'll be more solid.
Yeah.
Fair. It is a almost 4-hour recording, so just beware.
Yeah. Damn.
Yeah, I know.
I did not
Thanks
realize
for-
we were at this for 4 hours.
I also seem to be very quiet. I didn't do much of an audio test, so you might have to bear with me on that regard. But
yeah, that's fine.
let me stop the recording though.